Hey, it's Bruno here. Thanks a lot for taking care of little Timmy. He said he had a lot of fun with you, and he said that you're pretty cool. Anyway, let's get back to work. We have a big client here, big hospital client, and they've heard about machine learning, and they're willing to invest some money in experimenting with machine learning and seeing if we can build a model for them that might help their doctors. They have some data on heart disease, and they want to see if we can build a model that will be worthwhile to them. So can you create a report for them? They're not very good with machine learning, so obviously the more information we can provide them and not make it too technical, the better it is. You can do that? You're the best. All right, everybody. We just came off from a really tough section, which was Scikit-Learn. It was a lot to learn. We know that. I remember when I first learned Scikit-Learn, it was extremely overwhelming. It felt like I will never, ever understand the entire library. But as you saw, what Daniel does is he goes to the documentation. He searches Google. Anytime he has questions, he looks for the answer. That's part of our skill as programmers, as data scientists. We're able to solve problems that other people might have difficulties with. We're problem solvers. So over this project, we're going to repeat what we did with Scikit-Learn, but actually formalize it inside of a project so that now we have the skills and the tools necessary for us to build models around real-world problems. And we're going to build it in a way that actually mimics real-life work. So some of these reports are actual reports that Daniel and I have worked with before. And you can use these reports and this methodology to demonstrate to your future employers why they should hire you, or use it in your current role as a template for any future problems. But we got a lot to cover, so let's get started.
Welcome back, and I couldn't be more excited for this section. You know why? Because we're going to finally start getting hands-on with an end-to-end project. Putting all the tools that we've learned so far and the processes and the frameworks and whatnot, we're going to put them all together. We're going to make something of it. We're going to work on a project specifically with structured data, or a couple of projects actually. And so you might be asking, what is structured data? And well, we've actually been hands-on with structured data throughout what we've learned so far. Basically, structured data is whatever you can fit into this sort of structure. And what structure is this? Well, this is rows and columns, or something like a pandas data frame, or something like an Excel spreadsheet, or maybe a Google Sheets document. And so with our heart disease dataset that we've been working with as kind of a demo, on the left-hand side, you could have something like patient IDs, and in the middle, you might have some feature variables, such as details about the patient, their weight, their sex, heart rate, chest pain. And then on the right-hand side, or somewhere in the dataset, you may have a target variable, the thing you want to predict. And that's in essence what we're trying to do with machine learning. We're trying to learn some patterns in feature variables and how those patterns relate to a target variable. And that's what we're going to do throughout this section, is work on structured data projects which take this sort of approach. Getting a machine learning model to learn patterns within feature variables, and then using those patterns to predict some target variable. Now, how are we going to do that? Well, we're going to put this bad boy into play. We've seen it a few times already. We'll go through it step by step, the data modeling section of a machine learning project. So this is where we already have some data. We're going to go through, we're going to define what our problem is. What problem are we trying to solve? Is it classification? Is it regression? Is it something else? What data do we have? We'll look at the data set. Where might that actually come from? What defines success for us? So if we're working through a machine learning project and we're working on machine learning proof of concept, what level of success do we have to get to before we can say, okay, this may move from proof of concept into actually being deployed? What features should we model? So we have a look again back at the data, and are there certain features of the data that should take more precedence over others? What kind of model should we use? So we looked at this a little bit in Scikit-Learn of how to choose a different machine learning model for different problems. And then finally, what experiments could we try? So what have we tried? What else can we try? And the whole thing here, this is an iterative process. That's the main thing to remember. And then again, if we go here, we've got some tools that we can use for each step of the pipeline. So if this whole overall pipeline is data science, well, the tools we're going to focus on are Pandas, Matplotlib, NumPy, Scikit-Learn, and Jupyter, at least for the first project. We've got some green boxes highlighting the ones that we're going to be focused on. And we've already been hands-on with some of these and we've seen what they can do, but now it's time to combine them all in an overall project setting. And there's one more diagram we have to look at. Well, this is the steps we're going to take to set up a new project, and the steps you could take with almost any machine learning project. And so far, we've got our computer, we've downloaded and installed Miniconda, we followed this, but this is where we're up to now. So this is if we have our computer and we have Conda or Miniconda. We're going to start a new project and then create a project folder, and within that folder will live some data. We're going to create an environment similar to the one we've already been working in. And then within that environment, we can create our workspace in the form of a Jupyter notebook. And then within that workspace, we can perform data analysis and manipulation using tools like NumPy, Pandas, and Matplotlib. And then we'll start to look at how we can build or use machine learning models within Scikit-Learn. So Scikit-Learn has those pre-built machine learning models that we can use. We're going to see how we can apply those to our problem. So you might be wondering, of course, where can you get help? And the first step is to, because we're going to be working through this project together, is to follow along with the code if you can. If you fall behind, don't worry. It will be available to you through some sort of resource, through some sort of link in the place where you get those extra resources. If you are following along, try it for yourself, or if you are going along with it at a different time, make sure, if in doubt, run the code, right? That's the motto here. If in doubt, run the code. If you're curious about what a function does, remember you can press Shift-Tab within the brackets of a function to read the docstring. That will give you a brief overview of what the function does. And then don't be afraid. If these 3 steps don't work, don't be afraid to search for it. Right? You'll probably end up in places like Stack Overflow or the documentation. I've put both documentations here for Scikit-Learn and Pandas because we're going to be using a few tools here. So you might even have to look up the documentation for NumPy or something like that, another tool that we're using, maybe even Matplotlib. But wherever you get stuck, don't be afraid to search for it. What separates a good data scientist from a poor one is one that doesn't ask questions. So a good data scientist is just the one that keeps asking more and more questions. A good machine learning engineer is just the same as a normal machine learning engineer, but they ask more questions. And this is where the try again comes in. So once you've searched for it, once you've figured out something, once you've read something, don't be afraid to take it back to your notebook and try it. And then finally, as I said before, what separates a poor machine learning engineer from a good machine learning engineer is the questions that they ask. So never be afraid to ask a question. You might do this on the forum space or on the Stack Overflow section, wherever you see fit. So, without any further ado, let's jump in. I'm really excited. I hope you are. Let's get our hands on our first end-to-end machine learning project. So in the last video, we saw this little chart here and the steps to take in a new project. If we've been through this, if we've got our computer, we've downloaded and installed Miniconda that we did in a few sections ago. Now we're up to here. We want to start a new project. So how exactly would we do that? Well, that's what we're going to cover in this video. We're going to work through here, start a new project, create a project folder. Yep, we'll do that. We'll get our data ready for the project that we're working on. We'll make an environment. We'll probably want to create an environment that uses much the similar tools that what we've been using in our past environment. We'll make sure that environment works by starting up a Jupyter notebook. So if we come back to the desktop, I'm going to start up a terminal here. And so how would we go about it? If I've been working you might be working somewhere different, but for me, I've been working, so right now I'm going to change directory onto my desktop, into my ML course folder. And if I check in here, I've got a few different things going on, so a few different folders. But we've been working out of the sample project folder, or at least we have in the last few videos. So if I go into sample project, and if I ls there, which stands for list, I list all the things that are in here. So we can see there the introduction to Matplotlib, NumPy, Pandas, Scikit-Learn. And the thing is about this folder is that we've got an env folder in there. And now in this env folder, it's hard to say actually, env, env, short for environment. In this environment folder contains all of our tools. And if you remember way back when, if not, that's okay. We created that environment using Conda. So create an environment collection of tools using Conda. And so what we might want to do for this new project is if we go back up to where we were in the ML course folder, if I wanted to start a new project, we might want to create a project folder. That way, if we're in a new project, say for example, the one we're going to work on now, which is working on classifying whether a patient has heart disease or not, we might want to create a project-specific folder for that. And then within that folder has all of these little tidbits here, so that if we needed to share our work, we could share this folder by itself, and then hopefully someone on our team or someone else could replicate what we were working on because it's all contained in one folder. So let's do that. So if we go here, maybe we go make dir, and we'll call it, let's go project heart disease. Oh no, we'll go heart disease project. And in sticking to our nomenclature, we might use hyphens instead of underscores. So we'll do that. Make dir stands for make directory, heart disease project. Now if we go ls, we've got a folder, heart disease project. So if we cd'd into that, so change directory, heart disease project. If we ls, there's nothing in there. But we want to create an environment folder like we've got up here, in here. And how then would we replicate if we went back to our sample project folder and we ls there? How would we replicate this environment? Because we know this one works because we've been working through these notebooks. And what I mean by replicate environment is that we want to use the same tools in our heart disease project as we have working through all of these introductory notebooks. So I'll show you one way that you could do it. So we first have to activate. So if we go conda env list, we first have to activate our sample project folder or environment. So let's do that. We've seen this before. Conda activate. We'll copy this path, or we could just type it out. users/daniel/desktop/ml course/sample project. Wonderful. So now that environment is activated. We can tell that because base has changed to this. And now what we want to do is we want to create a new environment based on this one. So one way to do it is to export everything that's in this N folder as a YAML file. And what a YAML file is basically a text file of instructions of how to create a new environment based off this one. So let's see it in action. We can do that by running the code conda env export, and then this little symbol, this arrow, this greater than, or I never get these correct, greater than or less than. So this is, the way I think about it is, this is greater than what's on this side. Doesn't matter. This is like an arrow in this case. So it's conda env export, like an arrow pointing to the file you want to export it to. So in our case, we're going to call it environment.yaml or YML, which stands for YAML. The actual way to spell YAML is YAML. If you see either of these, YML/YAML, they're the same thing. If we do that, beautiful. We get a whole bunch of different outputs here, lots of warnings. So if we go ls, we should have an environment.yaml file. So if we look at that, if we go vim environment.yaml, so this is showing us what's in our YAML folder. These are all different dependencies, so conda packages that our previous environment is built upon. So see there, Scikit-Learn equals version 0.22, wonderful. We got Seaborn, wonderful. We got Python. We got a fair few things here. Now to exit Vim, we can press escape and then colon, see how it appears down here, and Q. Excellent. Now to create a new environment, we can deactivate the current one. So conda deactivate. So we can see now we're in the base, we're back to base. And to create an environment from a YAML folder, we're going to change back into our new heart disease project folder. See here, there's nothing in it. Now we're going to run the command conda env create. See how we're in the heart disease project folder. We'll run this command in this folder. So conda env create prefix dot slash env for env, and then -f for file. And then now we're going to pass it the path to our YAML folder, that file that we just created. So dot dot, it's in the directory above, environment.yml. Beautiful. And now running this is going to create an env folder within the heart disease project file. Now, doing it this way ensures that we get the exact same tools as in our sample project env. The other way we could do this is the one we've seen before, is by just going conda env create prefix dot slash env and then passing it the tools we want. Scikit-Learn, pandas, numpy, matplotlib, Jupyter. We could do it that way. But in this case, we want to make sure we have the exact same tool set for this project that we've been working on. So that's why we'll run the command conda env create prefix dot slash env -f, and then we're going to pass it the path to our environment.yml file. And we'll hit enter. Now, this is going to tell Conda to go to the internet and download all of those tools that we need, such as pandas, scikit-learn, matplotlib, all the specific versions that we've been working with in our introduction series. So while this runs through, we might speed up the video and I'll see you when it's done. Beautiful. That's what I'm talking about. So we've been through that. So basically Conda's just gone to the internet, grabbed all those tools that we need. We get a success message here saying that all these execution and transactions are done. And to activate the environment we just created, we can use this. But what we might do is just go conda env list to see what environments we have. So now we can see here in users, Daniel, desktop, ML course, in our heart disease project file, we now have an env file. And to activate it, we can run. Make sure you've got no other environment activated. So we're on base here. So we go conda activate. We're just going to run this code here that it's told us. Users /Daniel /desktop /ML course. Now again, of course, your path might be different. I'm just showing you an example one of what mine looks like for this heart disease project that we're going to work on. If we hit enter, we notice that base changes to this path name, so we've activated the environment. And now we're in the heart disease project file. So to test it out, we can go Jupyter Notebook. And this should bring up a Jupyter Notebook in our browser. Beautiful. If we look here, we've got the env folder. So in there, we've got a whole bunch of different stuff that Conda has created for us. And so if we go back to our keynote, what have we done now? So we've started a new project. Yes, tick. We've created a project folder. Tick. We've created an environment, a collection of tools, and we have access to Jupyter, so we have our workspace. What we're missing now is a data folder. So we can get that. What we're going to do is if we come back to Finder, I'll show you what mine looks like, where the data is. So if we go here, ML course, we've got this heartdisease.csv. We've worked with this file before. We've worked with this comma-separated value file. So I'm going to move that into my heart disease project. And if you don't have this file, that's okay. There'll be a link in the resources section where you can download it. And so now we're almost ready to go. If we come back, we've got a project folder. We've got some data in the form of a CSV. It may be in a different style for depending on what project you're working on, but in our case, we're using CSV. We've got an environment to work with, and we've got a Jupyter Notebook. Beautiful. Now it's time to get our hands on, create a notebook, and start performing some data analysis and manipulation, and then some machine learning with the tools we've used so far. Beautiful. So now that we've got our environment set up, we've got our Jupyter Notebook running, or a Jupyter Notebook server running, we can create a new Jupyter Notebook and get started on some code. So let's load that up. I'm going to maximize this window. So we'll give it a name here. We'll go end-to-end, something nice and simple, end-to-end heart disease classification. And in good communication style, we'll put a markdown heading and go something simple, predicting heart disease using machine learning. And then a little one-liner. So this notebook looks into using various Python-based machine learning and data science libraries, which are our tools, in an attempt to build a machine learning model capable of predicting whether or not someone has heart disease based on their medical attributes. Whew! So that's probably more than one liner. We could probably concise that a little bit, but that's not our focus. Our focus is writing code and applying it to the framework here. So this is what we want to work through. This is what we're starting to do. We're starting to apply the tools that we've learned to our machine learning framework in the scope of a full-blown end-to-end machine learning project. Oh, I hope you can feel the excitement. So, how do we start off? Well, the first thing is probably good to outline our approach. We're going to take the following approach. So the first step is problem definition. We've kind of done that with the opening line. So problem definition 2 is data. We'll look at what data we're going to use to work through this problem. We've kind of already seen it in previous videos, but again, for completeness, we'll just have a little overview look at it here. Then we'll go evaluation. We'll define quickly what an evaluation metric means for us, like what defines success. For this, if we were to deem this project a success, this machine learning proof of concept, could we predict heart disease using machine learning? What would we need as an evaluation metric as a bare minimum? Features. So what features of the data are we going to be most focused on, and even which contribute most to the model, which is step 5, modeling. And finally, step 6 is experimentation, and realistically, the whole thing is experimentation. So this is what we might start with. And again, if you're quite experienced here, you might just start diving in straight to the code. You might know what to do. But for us, because we're still learning, we're still figuring out how to approach different problems, we set up this framework and then we figure out how we can use our tools at each different step. So let's go back. First and foremost, problem definition. We've kind of already done it here, but in a statement that we could tell someone else. So in our case, we're doing binary classification, so whether someone has heart disease or not. So there's only 2 classes. Remember, classification is predicting whether something is one thing or another. So in a statement, we want to, or we'll put it in a nice little quote. So given clinical parameters about a patient, can we predict whether or not they have heart disease? Wonderful. And then 2 is the data. Now, if we come up here, we know that our heart disease data is in a CSV file already. And if we click on that, it's going to load up. It's pretty hard to read here, so that's why we're going to import it soon using a pandas data frame. But if we go up here and if we go UCI heart disease dataset, this is where we find about, and this is step 2, by the way, data. This is where we're finding out a little bit more about what data we're actually using. So this is where you could come and download it from. This is the original source for it, the UCI machine learning repository, which has a lot more different data sets in here that you can kind of work on and use for example problems like what we're working through. But to get it in the CSV format, it's already been formatted, and that's on Kaggle. Now you can go to Kaggle as well and get a lot more different data sets. Over here, it's got a little menu. It's got data sets there. You can even search for different things. But this is where I came to originally at this data set. You can download it here. So if you click download, it's going to tell us a little bit more information about the data, some attribute information such as what the different columns stand for. If we keep going, we look here, we see that the different columns, this is where their different values are. So what this is a data dictionary. And we're going to see this in a second. This will come in handy. What we might do actually is see if we can copy this and take it back to our notebook. So this is a data dictionary. So we might go here, create data. This is getting a little ahead of ourselves. So if we go there, boom, that's what we can use to reference what the columns are in the data. So if we go here, data, we could probably pull out something from here. So if we copy this, so this database contains 76 attributes. Well, Actually, our data set only contains 14, but then we read here, but all published experiments refer to using a subset of 14 of them. Okay, wonderful. And so then if we went back to the UCI heart disease data set, we get a little bit of information here. So only 14 attributes used. Now, you won't always do this for every project that you work on, especially if you're working within a company or within a team. The data set might be given to you by a customer or by a client. But for the problems that we're working on, because we need access to open source data, that means data that everyone has access to, we can find them publicly on the internet. But then again, the process is very similar no matter what data set that you're working on. It's all about getting it in the right format that you can work with it in your Jupyter notebook. We might put in here the original data came from the Cleveland database from UCI machine learning repository. There is also a version of it available on Kaggle. And so what you might do is copy that in there. Beautiful. And we'll also copy that in there. And we could tidy this up later, but this is just some information about the data. Where did it come from? What data do we have? And so we go here, number 3, evaluation. So if we were actually working on this project, we wanted to implement this. Let's say we were a hospital who wanted to be able to implement this as a machine learning model, as an application on the front desk. If someone comes into us and we're a nurse, we're measuring these different parameters about them. So we found out different patient attributes. What metric would we need to judge our model as being effective, as being able to use in play? So if we're trying to classify whether someone has heart disease or not, because that's pretty significant, we'd want a very, very accurate model. And so, for example, I'm just going to make a number up. So you might say something like, if you can reach 95% accuracy at predicting whether or not a patient has heart disease during this proof of concept phase, which is kind of what we're working through here, then you might pursue and try to really get into the hands of other people. So that's the essence of what we're going to work through here, is we're building a machine learning proof of concept. The reason why I say proof of concept is because oftentimes machine learning projects will start out as trying to figure out if there are even enough patterns in the data to be learned by a machine learning model. And if there are, then you might pursue the project further and get it into production or into some sort of application. So again, this is just another benchmark we might set ourselves as a goal to work towards at the very beginning of a project. And it's not set in stone, this may change. It's just something you might reflect with your team, like, hey, if we're going to spend 2 weeks working on this machine learning project, what figure would we have to end up with for it to be pursued more? So let's do that. So if we can reach 95% accuracy at predicting whether or not a patient has heart disease during the proof of concept, we'll pursue the project. And this may be another thing, right? Someone might come to you at a data science company or something like that. Someone from another team might go, hey, we've got this data set. We want to measure how many of our customers are churning. And we want to see if we can build a machine learning model to help us out. And then they may say, hey, do you want to work on a proof of concept like similar to what we're doing here? And this is how you might set it up. You might start out by going problem definition, figure out if a customer is going to churn or not. Where does the data come from? It comes from our customer database. What's our evaluation metric? Well, if we can figure out if a customer is going to churn at about 80% accuracy, then we might keep pursuing this and actually get it into our production pipeline. That's an example kind of workflow of the first 3 steps. And then finally, step 4, well, not finally, we've got a fair bit more to go. Features. So if we come back, so we've done this, we've done evaluation, what defines success? We go, what features should we model? This is step 4. So this is where we're creating a data dictionary. And what I mean by that is you may be able to create this on your own by doing a little bit of research. So we might put this in bold. And again, we could tidy this up by putting these all in dot points, but they'll start to make sense in a second once we actually see the data we're working with. Actually, yeah, we might type this into, turning this into dot points. So now we've created our data dictionary. This is something that you may find through your own research, like we've done here, finding out about the data here, finding out about the data, or you may create it with the help of a subject matter expert. And what I mean by that is, say, for example, you had that team come to you with a whole bunch of customer data on who's going to churn or not. Churn meaning that they're going to leave or stop using your product. And they may tell you what different features of the data mean. And so I'll put here, this is where you'll get different information about each of the features in your data. So essentially, when you start to work with the data, you won't be a complete novice. You'll have some idea of what's actually going on or what each section of the data means. And this will make a lot more sense when we look at our data in the flesh, when we import our heart disease CSV file into our Jupyter notebook, which is what we're going to do in the next video. So these first 4 steps, 1, 2, 3, 4, problem definition, data, what data do we have, evaluation and features, don't necessarily have to take that long. So we've just gone through all 4 of them in about 10 minutes, because what we want to do is get hands-on with the code and let the code and data speak for itself rather than trying to just think about it here. We want to see it in action. So that's what we're going to do in the next few videos. Welcome back. So while you were gone, in between the last video and this one, I've kind of tidied up this data dictionary here, so it looks a bit better now. And don't worry, you'll have a copy of this in the resources section, so you're not going to be missing out on anything. But just where we left off, we talked about features, which is step 4 in the machine learning pipeline that we're using, or the machine learning modeling pipeline that we're using. And this is where you'll get different information about each of the features in your data. You can do this by doing your own by doing your own research, such as looking at the links above. That's what I did here to kind of tidy this up. Reading between this information here, so attribute information, as well as UCI dataset webpage. If you go through here are all 76 attributes, but realistically we only used 14, so only 14 attributes used, and that's what this data dictionary is. So basically a data dictionary just tells you about the data that you're working on. Wonderful. And so now, where are we up to? If we check back, we've worked through 1, 2, 3, 4, but have we really? So we've just kind of done it in thought. So now it's time to apply the tools that we've been going through to this section, right? So this data analysis section. So let's do that. Let's get our tools ready. So we'll create a heading here, preparing the tools. We're going to use pandas, matplotlib, and numpy for data analysis and manipulation. Wonderful. And so at the start of every notebook, what you might do is import, this is what you'll probably see out in the wild, is a big chunk or one big Jupyter cell importing all different tools at once. You don't necessarily have to do it this way, but it's kind of industry standard to do it this way. So let's see what that would look like. Import all the tools we need. So what we might do is make little subheadings here. So that way when we're working through this step-by-step process, we've got all the tools that we need. And now, again, a project might not start out like this. I'm only doing it this way because this is what you'll see with the sort of finished project. What you'll more regularly do is kind of how we've been working with it in the past, is just import a tool as you need it. So when you see this big block of code that I'm about to type with all the imports and all different tools and whatnot, you might look at it and go, holy goodness, I'm not sure what's going on with everything there. But that's okay. What you'll do is, because you've got the framework now, you've got this, and we've seen different ways that we can apply different tooling, you'll be pretty familiar with all of the functionality that we're going through here. And if not, that's perfectly okay. You know where to look and you know where to get help. So let's do this. We'll go regular, EDA, and plotting libraries. Here's where we're going to import NumPy. EDA stands for Exploratory Data Analysis, by the way. Got to learn not to talk in acronyms. We coders like to shorten everything. So import NumPy as NP, import pandas as PD, import matplotlib dot pyplot as plt at plt. Come on, Daniel. Import seaborn as SNS. So seaborn, remember, is just that plotting library built on top of matplotlib. Matplotlib is the base plotting library that we're going to be using. So I'm going to do matplotlib inline because we want our plots to appear inside the notebook. So this is what this little magic function does with that percentage sign there. And then we want to import models from sklearn or scikit-learn, also known as sklearn. You're about to see that in a second. So from sklearn, we want a linear model, import logistic regression. Now, if you're wondering where these models came from, remember we've got scikit-learn model map, choosing the right estimator. Wonderful. So we followed this along in a previous section. We're working on a classification problem, so we're only going to be importing classification models. So from sklearn.neighbors, we're also going to import another model here. So k-neighbors classifier. And you'll remember this one, ensemble. You might not have seen the first two, but that's okay. We'll talk about them when it comes to it. Random forest classifier, we have seen that one. And then we're going to go model evaluations. We're going to go from sklearn.model selection, import train test split. This is going to help us split our data into training and test sets. We'll also import cross-val score from here. Now, if you're wondering how I know all these, it's because I've had some practice. And if you're looking at this going, holy goodness, there's a lot of things to remember to import. And you're like, oh, that's what I'm saying. I'm agreeing with you. But machine learning is a very broad field, and there's a lot of different ways to do similar things. But after some hands-on practice, like what we're going through now, you'll start to get a bit more familiar. And again, it's no rush. I still have to look up things. So I've done these on separate lines, these two. I could have done them on the same line because they're from the same module, but just to keep it a little bit tidy, a little bit Pythonic, we want to go here from sklearn.metrics, import confusion matrix classification report. Well, they may be familiar from the evaluation section of the scikit-learn section. We go here, import. We want to get precision score because we're thinking in our head, this is a classification problem. What metrics can we use to evaluate classification models? F1 score from sklearn.metrics, import plot ROC curve, because we want a ROC curve. Whoa. You might be looking at that going, Daniel, that is a lot of stuff. And it is. This is 21 lines of imports minus a few comments. But this is the tools that we're going to need. So if we come back here, we may still even need more. I might have missed some. But this is kind of what you'll see at the start of a notebook, is because once we've set it up, we want to approach these and we want to minimize our time between experiments. So that's why we're getting all our tooling ready right at the top so that we can get hands-on as soon as possible. So we've got pandas, we've got matplotlib, we've got NumPy, we're working within a Jupyter notebook in our Conda environment. We've got scikit-learn, and now we're going to work through the data analysis section. So that means basically importing the data, having a look at it, and trying to become ourselves a subject matter expert, which is just someone who knows about the data, like a fancy word for someone who knows about the data. That's what we're trying to do in these 3 steps here. So without further ado, let's hit Shift and Enter, import our tools. Fingers crossed. If we've set up our environment to work, these should all import correctly. What are we getting here? Something wrong. Runtime error. MP ufunc size change. May indicate binary incompatibility. Expected 192 from cheader got 216 from PyObject. I've actually never seen that error before. So this is what you come across, right? These type of things, even after you've had some experience, you'll come across these things. This warning. So we're just waiting on to make sure that this cell runs fully. It's already given us a warning. Oh, we're getting another warning. Here we go. mp.ufunc. Now we might let this cell run out, as in finish, because it's going to take a little while. unrecognized arguments. Maybe I can't put this. This needs to go above here. There we go. Will this import? Yes, it should. And now we're getting no warnings. That's interesting. Well, that's the surprises that you'll get from day-to-day running, working with different machine learning code and different code in general, is sometimes it does things that you don't really expect. And so that warning has gone away. If it does come back in the future, we'll probably deal with it then. But for now, we'll assume that we've got our tools ready. Now we can start applying them. Now that we've got all our tools ready to go, the first step is to load the data in, because without data, how are we supposed to use our tools, right? So we go here, load data, make a little heading. Then we're going to set it as df. So df is usually short for data frame. So pd.readcsv, because we've got our heart disease CSV folder in our current working directory, we can just go pd.readcsv. We're going to pass it. Can we do tab autocomplete? heartdisease.csv. Beautiful. And then we're going to have a look at it. Wonderful. That seems like it's imported great. We've already had a sneak peek at this before, but we might go df.shape. This is going to tell us how many rows and columns there are. So essentially, we have 303 examples, which is rows, and this is columns. So this comes in the form of rows, columns. Now, once we've got data loaded in, what's next? Well, that comes data exploration, aka known as exploratory data analysis, or EDA. Once you've imported a dataset, this is where you want to start to explore it. Now, there's no set way of doing this, but what you should be trying to do is become more and more familiar with the data. So you can compare different columns to each other, compare them to the target value, refer back to the data dictionary, try and figure things out. What your goal is to become a subject matter expert on the data set that you're working with. So the goal here is to find out more about the data and become a subject matter expert on the data set you're working with. Now, this is because, so if someone asks you a question about it, you can give them an explanation, and when you start to build models, you can sound check your model to make sure they're not performing too well, such as like overfitting, or they might be poorly performing, such as underfitting. Now, since EDA has no really set methodology, what we're going to do, we'll write down a short checklist. So we can go, what questions are you trying to solve? So this is back to our problem definition. And then what kind of data do we have? And how do we treat different types? So this is like numerical versus categorical. In our case, all the data in our data frame is numerical. Now, remember, these steps aren't just associated with the heart disease data set. They can be applied to almost any data sets. What's missing from the data and how do you deal with it? Step 4, where are the outliers and why should you care about them? Now, outliers are values or samples which are so far away from the other samples, like in terms of if you were comparing one sample to another, if one sample was just completely outlandish, it might be an incorrect sample that someone may have made a mistake when they were logging that, or it may be an incorrect sample, just full stop. Or it may actually be that that's just an outlandish example and it should be included in your data set. Then finally, and again, this is a non-exhaustive list, how can you add, change, or remove features to get more out of your data? So it's kind of like an EDA checklist that you might want to start with as a bare minimum of what we're trying to figure out. How about we do that? So the first thing, we might check df.head, traditional way of looking at a data frame. If we wanted to look at the bottom, we might do df.tail. Wonderful. And then the next thing, because we're trying to predict this target variable, I probably want to figure out what's some information about that. So we go df.target, maybe we use this one. Remember, there's two different ways to access columns in data frames. You go df.target. or df target as a string. We can call value counts on that. So we'll go here. Let's find out how many of each class there are. So in our case, if we go back up to our data dictionary and we're trying to figure out what target is, we can see target is have disease or not. So 1 equals yes, 0 equals no. So there we go. So we have 165 examples where someone has heart disease based on their health parameters, and 138 examples where someone doesn't have heart disease. And so what we would think here is that this is a relatively balanced problem, meaning that we have quite a similar amount of examples in both classes. So that's a balanced classification problem. And so if we go here, maybe we want to visualize this. So if we go df target value counts, because we're always trying to be as explanatory. We want to explain the data in a way that both we and other people can understand. And visualizations are one of the best ways to do that. So kind equals maybe a bar graph, and then we'll pass it some fancy colors so that we know this is our graph. We'll trademark these colors. We'll go light blue, salmon and light blue. Let's see this. Oh, we'll put a little semicolon here so that output doesn't come up. There we go. Maybe we could relabel these as something. Maybe that might involve changing the values in the data frame. We won't do that for now. If we wanted to share this with someone, we could relabel that as heart disease and no heart disease. The next thing we might want to look at is different information about our data frame. So we can do that with df.info. What are the other columns got in them? Are there any missing values? So this is what this is going to tell us. So we have age, which is a non-null int 64. There's 14 columns, 302 entries. Sex is int 64. CP, what's CP? Remember, we can check our data dictionary. Come up here. Chest pain type. Okay. Typical at angina, atypical angina. Not actually sure what angina means. So this is where we're trying to figure out what our data is all about. So define angina, a condition marked by severe pain in the chest. That makes sense if we're dealing with heart disease data. Okay. So if we come back, see how there's no real structure to this? Like we're just kind of jumping back and forth. If it seems like we're bouncing around, it's because we actually are. And another way to see, is there any missing values? df is na.sum, because remember, one of our questions in exploratory data analysis is what's missing from the data and how do we deal with it? So are there any missing values? In our case, there's not, so we don't have to do anything about the missing values there. Then if we're still trying to find out more about our data frame, we might do df.describe, which is going to give us some numerical values about all of our columns. So we got count here, which is 303. That's how many rows there are. We get the mean value of age. So that means the mean value of all of our patients here is 54. We come through here. Okay, there's not too much there that we can really make use of for now. What we might start to do is compare different columns. So we'll probably save that for the next video. So save this one getting too long. So now we've got some quick insights about the data, right? No real structure here. We're just trying to figure out what's going on. We've read the column headings here. We've compared them to our data dictionary. We've seen how many examples of each target there are in this graph here, this visualization. Now we're going to start to compare different columns and try and get a bit more of an idea of where the patterns are within our data. So let's do that in the next video. Beautiful. Now we've found out a little bit more about our data frame. What we're going to do now is compare different columns to each other. And the reason being here is because this is helpful to help us start gaining an intuition about how the features, so these columns here, relate to the target variable. So that's what our machine learning model is eventually going to do, right? It's going to search through the different columns of our data frame and then figure out the patterns as to what target value is associated with values here. Now we could do much the same. If you just went through this row by row, you would start to gain an intuition about what values associate with what target value. But let's stop talking about it. Let's visualize it. So what we'll do, the first two columns we might compare are age to target. So we go here, frequency according to sex. So this is what we want to do. We want to compare the sex attribute to the target attribute. So what we might do is go df.sex.valueCounts. Here, there's no real pattern of how we're doing this. We're just kind of exploring the data. All right, so we see here, there's a lot more male to female. So female is 0 here, that number, and male is 1. The reason why I know that is if we go back up to our data dictionary, if we look here, sex, 1 equals male, 0 equals female. Wonderful. So we come down. So we know our data set is a little bit tilted towards having more males than females. If we wanted to compare the sex column to the target column, a handy function in pandas is the pd.crossTab. So let's have a look at that. Compare target column with sex column. PD crossTab. We're going to pass it df.target with df.sex. Beautiful. So this is going to give us some information here. And what can we infer from this? Well, what we could do to begin with, before we even build a single machine learning model, is make a simple heuristic. So since there are about 100 women, right? If we add up this, so if we see sex is 0, and this is comparing the target column to the sex column. So since there are about 100 women, and 72% of them, or 72 out of the entire amount of women, have a positive value of heart disease being present. So see here, the target is 1. So that means an indication that they do have heart disease. What we might infer based on this one variable, if the participant is a woman, so if the sample, if we come back up here, if the sample in our data is a woman, there'd be roughly a 75% chance she has heart disease. The reason being is because here we've taken about 100 or so. Again, we're just rounding here. And if we add these up, that's going to equal 96. But if we see here, just looking at this comparison between sex and target, 72 out of 96. So basically 75 out of 100. So what we're inferring from this, before we even build a single machine learning model, if a woman comes and we're trying to figure out whether she has heart disease or not, based on our existing data, based on our existing data set, 75% chance that she has heart disease. Again, remember, based on our existing data set. It might be different in the real world. And so if we look at male, there's about 200 in total, with around half indicating a presence of heart disease. So see there, 93, target equals 1. Where sex equals 1. When the sample is a male, 93 out of 207 indicate that there is heart disease. So if we looked at this, if the participant is male, we might predict around half the time that participant will have heart disease. And then if we average these out, we'd get 75% plus 50% over 100. You get about 62.5% chance that anyone, of course, this is always based on our existing data because that's the only patterns that we can find is with the data that we have. So based on our existing data set, this up here, if we were to see a random patient, we're making our decisions whether that random patient, a new patient we haven't seen before, we're making our decisions based on our existing data set. And based off this comparison alone, we might infer that there's a 62.5, remember, about 75% if they're a woman and 50% if they're a male. So we're just adding them together and averaging them. So 62.5% chance that they have heart disease. Now this is our very simple baseline. And what we're trying to do here is just form an intuition in our head about the data set, about how different features, in this case we're doing the sex feature, the sex column, we're comparing it to target. So if we would just use that one feature alone, if we were to expect a patient to come to us, we'll go, okay, any patient at all, there's a 62.5% chance that they have heart disease. And now with that baseline, what we're going to try and do is beat it using machine learning. So again, if this is a little bit confusing, don't worry, it's a little bit confusing when I first started figuring out patterns. But the main thing to remember is all we're doing is just creating an intuition. We're becoming subject matter experts on the data, or at least trying to. And so what we might do is make this a bit more visual. Create a plot of crosstab. We go pd.crosstab, df.target, df.sex, and then we can go .plot, and we'll do it as a kind of bar. We'll give it a fig size, just because we want it to come out. We'll go 10:6, so that's width and height there. And then we'll give it our famous color that we're going to work with, which is, we'll do salmon and light blue. Wonderful. Beautiful. So this is another visualization that we can start to get an idea. And it shows it a little bit more intuitively than just a crosstab. So if we look here, we've got target, which is 0, not heart disease. And this is sex, 0 or 1. So we can see that the people who don't have heart disease, there's far more male. And we can see here that the people who do have heart disease, now there are more males that do have heart disease, but if we look at the ratios compared to each column, so this one is male, blue is male, and the salmon color is female. If we compare these columns, we can see that the females who do have heart disease is about a 3-to-1 if you would just compare those visually. About 3-to-1, right? So that's where we're getting a 3 and 4 chance of a female at random having heart disease. But males, the ratio is kind of, and it's definitely not completely even, but it's a lot closer than what the females are. Wonderful. So if we wanted to add some titles to this, we could add some communication here, such as maybe we go plt.title, heart disease, frequency for sex, and then we go plt dot, maybe we add an X label, and we go 0 equals no disease, 1 equals disease. We might go plot Y label. We might put amount here. Then maybe a legend, because we might change this legend. See if we can update that to, rather than being 0 or 1, so we want to communicate this to someone. We're doing some data analysis. They don't know what 0 or 1 means. So we want to do female, male. Actually, I'll show you what this does before we even do it. So let's do that. We'll add a little semicolon here so we get rid of that. What are we missing out here? Oh, I forgot legend. That should work. Wonderful. So that's a little bit more intuitive. And so this is what I wanted to change here. I wanted to get them vertical. So what we might do is plot X ticks. These are X ticks here, little ticks that are labeling. So we go plot X ticks, and then rotation equals 0. This took us a little while to get set up, but really if you're going through this, you might breeze through it if you're going through it by yourself. But if we want to communicate it with someone else, we better design it in this way, because we may know the data ourselves, but if we just want to share this image so someone else has an intuition over the comparison of who has heart disease depending on what sex they are, they won't know what we know with the data. So that's why we're making our visuals as communicative as possible. All right, now that we've compared 2 columns, we've seen how to do it. What we're going to do in the next few videos is compare a few more. So take a little break, reflect back on what we've gone through here, maybe try compare 2 columns of your own. Usually you compare the target with a single column here, and you start to work out the patterns. Now for our next comparison, what we might do is try to combine a couple of independent variables, such as age, thal-ax, which is maximum heart rate, and then compare them to our target variable, heart disease. So if we have a look back at our data frame, so what we might compare is age, thal-ax, and target, all in one. And now if we go to check our different values for thal-ax, now the reason why I know this is max heart rate is because if we come back up in a second, so we can see there's a lot of different values here. So the length 91, if you call value counts on any column, and the length comes up as something, that means that there's that many different values in that column. So what that might be telling us is because there's so many different values, looking at it on a bar graph may not be the best type of graph, because if we look at this plot, there's only 4 columns here, and that's pretty interpretable. But when there's 91, that might be a bit harder to look at. So that's where we might bring in something like a scatter graph. Let's go back to our data dictionary and have a look at what thal-ac is. Come up here. Thal-ac, maximum heart rate achieved. And again, we're really just diving in, reading our data dictionary. Here you might just go through different columns, read them, which ones stand out to you, and try to compare a few of them with the target variable. And remember, if we come back to our data frame, these are often referred to as features or independent variables, and this is often referred to as the target or dependent variable. So that's what we're doing here. We're comparing independent variables to our target variable. This might seem a little as if we're jumping all over the place, and I know I've said this before. It's because we are literally just picking columns here that spark our interest. This one sparked my interest, and we're trying to figure out how they relate to the target. That's what we're doing. You may choose a couple of other columns. I'm just going through the ones that look most interesting to me. So let's make a little heading, age versus max heart rate for heart disease. And then we'll turn that into Markdown. Beautiful. So to compare 3, such as age, thal-ac, and heart disease, what we might have to do is create a plot with 2 plots on it. So let's start off first by creating another figure, plt.figure, and we'll pass it a fig size equals 10.6. Then we might go scatter. We might do a scatter with the positive examples first, so just bear with me for a second and we'll talk through what's going on while we're going through it. So plt.scatter, we want to see on this scatter the positive examples. So we could go df.age or df.age in brackets. They really mean the same thing, but I like to do it this way, df.age, and then in here we're going to do df.target equals, of course you couldn't do this if your column names had spaces in them, but in our case none of our column names have spaces. What this is doing is a subset of the data set. We're taking the age column from our data frame where this condition equals true, so where the target equals 1. So if we did that in a cell below here, df.age, df.target equals 1. So this is going to show us all the age columns where target is equal to 1. So that's what we want. Beautiful. And we also want df.thal-ac, which is maximum heart rate, df.target equals 1. Beautiful. And we're going to give it a color of salmon. What would this look like if we called that? Wonderful. So along here, we've got maximum heart rate and we got age. So what could you infer from this pretty quickly by just looking at it here? Well, you might infer that there's kind of a downward trend. So if you were to draw a line through there, just a straight line, it's all over the place, right? But it's kind of, you can kind of see the pattern going down here. The younger someone is, the higher their heart rate. That's the kind of trend that you'd be seeing there. That makes a little bit of sense, right? Now, these are positive examples. So these are patients, because we've got target equals 1, these are patients with heart disease. And so now we want the negative examples on the same plot. So scatter with negative examples. I'm going to go plt.scatter, and go df.age. All we're going to do is just copy what we've got above, but except target equals 0 because they're negative examples. This is without heart disease. thal-ac df.target equals 0. Wonderful. C equals, I'm going to go light blue. That's the color scheme we're set up for now. Beautiful. So now we've got positive and negative examples on there. And again, they're kind of all over the place, but if you were to look at the trend, the line kind of goes down for both, but again, you can't really split them. This is where our machine learning model will have to take over from our ability to have a look at this. So if you were to look at this, I just put a semicolon there to stop that little matplotlib output. If you were to look at this and you were trying to decipher what's going on here? What was the maximum heart rate of someone who had or didn't have heart disease? The salmon versus blue dots. Blue dots are without heart disease, salmon are with heart disease. If you had to decipher this, it'd be pretty hard, right? Because these are all so mixed up together. Maybe you might infer that there's some sort of pattern. There's a fair big cluster here. There's a big cluster here. But really, I can't really tell a pattern. Maybe if I had some more time to look at it, I could find something. But this is where machine learning is going to come into play. The patterns that you can't necessarily see straight away, machine learning is going to dive into the data. It's going to form some calculations and figure out these patterns that we can't really see. Again, if we had enough time, maybe we'd find something. But we're machine learning engineers, we're data scientists. We prefer that the algorithm does the job for us. So what we might do is add some helpful info just to make this plot a little bit more complete. So plt.title, heart disease in function of age and max heart rate. And then plt.xlabel, down the bottom is the age. And then plt.ylabel, this is going to be max heart rate. And then we'll add a legend so people can understand which dot is which, and they're not just thinking about, whoa, what's going on here with the salmon and light blue dots? Amazing color scheme, but I'm not sure what's happening. And we'll put the semicolon there instead of there. Wonderful. So that's looking a little bit better. But again, you let me know if you can see some sort of pattern. But to me, all I can really see is there's a bit of a downward trend. So as someone gets older, their maximum heart rate decreases, which kind of makes sense. Again, when you're exploring a data set, you won't necessarily always find patterns to begin with. We're just familiarizing ourselves with what's going on. And so because we've just done the age, what we might check out is what's the distribution of the age. So to do so, we'll go check the distribution of the age column with a histogram. Now the distribution is another word for spread of the data. So we can kind of see here that there's almost an even spread. So you may recall what kind of distribution an even spread of data has. And if you don't, that's perfectly fine. It took me a while to understand this as well. It took me a long time actually, and I still have to research. So this kind of distribution here is otherwise known as a normal distribution. And if you were to really say what kind of normal distribution is, we'd look at this perfect normal distribution. Let's have a look. Let's go normal distribution is going to look like a bell curve. So see something like that. So if we come to ours is very close to that shape, but it's kind of swaying towards the right. So we can see that most of our population or most of our samples, their age is around this big mid gap here. And we don't have that many around the 30-year-old age or past, this might be 80 up here or something like that. We don't have many past there. The majority of our data set are within the 50 to 60 range. And so this is what you might want to do for a bunch of different columns, is check the distributions, check the spreads. If we did have someone out here that was like 150, that would maybe be some type of data that we'd have to clean up, because I'm not sure if anyone's ever lived to 150. Or if we had someone down here that was maybe 5 or something like that, we'd also have to think about, okay, is that something we want to include in our data set? But this is going to be different column to column. So we're just checking the age here. It's a normal distribution. We might do the same for other columns, but the way you sort of think about samples out here is they're referred to as outliers. And now, how will you tell that if there's any outliers? Well, distribution plot, this histogram, is one of the best ways to do it. So if you're getting some weird results, like some weird results in terms of your machine learning models later on, it may be because there's outliers in the data, and that's where you'll have to check different distributions of each columns. So that's one way to do it. Now, what we might do is compare another two columns. So if we come up here to our data dictionary, I saw this one before, the chest pain type. And I thought that would be interesting to see. So if we got here 4 different types of chest pain. So chest pain related, decreased blood supply to the heart, chest pain not related to heart, typically esophageal spasms. So I guess that's like your esophagus, which is, I think, that tube from your mouth to your stomach or something like that. Asymptomatic, chest pain not showing signs of disease. Okay, so this will be pretty interesting, right, if we compare this to the target column. So chest pain versus target. So does chest pain relate to whether or not someone has heart disease? So let's come down here. We'll go make a little heading. Heart disease frequency per chest pain type. And what we might do actually is just remind ourselves, copy our data dictionary for chest pain so we can remember what each different value is. So if we come in here and we'll copy this, Shift and Enter, we'll bring it down and we'll paste it here. Wonderful. So this is what we're going to compare. We can do that with fairly quickly with a PD crosstab, df.cp, df.target. Okay. So if we look at this, what would we devise in here? It seems as chest pain goes up, so does whether they have heart disease. But if we get 0 chest pain, there's a lot more that don't have heart disease than do. But if we get 2, there's only 18 with 0, so don't have heart disease, but 69, so nearly over 3 times the amount that do have heart disease. So this is non-adrenal pain, typically, non-heart related. Well, that's interesting that it's non-heart related. And so these are the type of patterns you'll start to find out in your data. Some make sense. That doesn't really make sense to me. Non-heart related pain, yet more people have heart disease with 2 than not. And so these are the type of things you might be wanting to discuss with a subject matter expert. If you're looking through a data set, such as us looking through this heart disease data set, and I'm not a doctor, I'm not trained medically, I've researched some things about health, but I've no idea about chest pain. So if I got this data set off someone from a medical profession, I'm trying to use machine learning to figure out whether someone has heart disease or not, and I'm coming across these patterns that I don't really understand, that's where I'd probably reach out and go, hey, to a medical professional, or I do my own research, such as looking up what these actually mean. We did that before, defining angina. Going, hey, I'm seeing this in the data, but can you shed some light? It's kind of confusing to me. Is this correct? Is this not? That's the kind of the insights that we're looking for, is both patterns that make sense to us, such as the normal distribution of age, such as the declining max heart rate as someone gets older. This one maybe doesn't make as much sense. Is heart disease more prevalent in women than it is males? So this is the type of questions that we're trying to get. We're trying to formulate an idea in the data by not finding answers, but finding questions that we can ask. And so what we might do is make this a little bit more visual, as we've done before. Make the crosstab more visual. PD crosstab df.cp df.target. We're just writing what we've got above there. .plot. Same plot again. We might do a bar because there's 4 different values here versus 2 different values there. So we should be able to look at it fine on a bar graph. Fig size equals 10 and 6. Wonderful. And we're going to use our favorite colors. Color equals, what are we using? Light blue, salmon. Actually, I think the order was the other way around. Maybe we did salmon first, then light blue. Doesn't really matter. Beautiful. Then we're going to add some communication. plt.title. Heart disease frequency per chest pain type. Then we go plt.x label. I'm going to do chest pain type. And then on the y is plt.y label amount. Beautiful. plt.legend. We're going to put on here no disease. And then we'll finish it off with, again, we're going to make sure that the X ticks are vertical so it's a bit easier to read. Shift and enter. What do we got? PyPlot has nothing. Y label. We got a little typo. Beautiful. There we go. So that's a bit more visual. So there we're just turning our crosstab into a graph here. Now this is something that we could take pretty quickly to someone and go, hey, what's going on here? Chest pain type has way more accounts with the disease than chest pain 2, that is. And it's supposed to be non-anginal pain. So typically esophageal, that word is very hard for me to pronounce, esophageal spasms, non-heart related. So this is, again, raising questions from the data. That's what we're trying to do in this exploratory data analysis. All right, so we've got a pretty visualization there. What we might do next is check out the correlation between independent variables and our dependent variable. So again, if we have a look at our data frame, this is what you want to be jumping in and out of, right? Just using df head to quickly have a snapshot of your data frame. These are our independent variables, remind ourselves, and we're trying to use them to predict targets. So we'll see how we can compare those, and we're going to use a correlation matrix, but we'll see that in the next video. All right, now we've done a little bit of EDA or exploratory data analysis. We're going to do one more step, and that is building a correlation matrix. You might be thinking, what is a correlation matrix? In layman's terms, it's a big table of numbers telling us how each independent variable is related to each other, aka these columns here, how do they interact with each other? Are they a positive correlation or are they a negative correlation? Now, let's not talk about it for much longer because we want to see it. We want to see what is happening. So let's go make a correlation matrix. And to do so, we can use df.core. If we hit Shift-Tab here, compute pairwise correlation of columns, excluding NA/null values. Well, pairwise correlation, that's just basically saying compare each of these columns to each other. Well, let's see it in action. If you're looking at this for the first time, quite confusing because there's a lot of numbers going on here. Okay, you can see the columns are on the rows as well as the columns. And the diagonal here is 1, 1, 1, 1. There's a lot of decimals, and some are negative and some are positive. What we might do though, instead of staring at this and exploring it for a little bit, we might make this a little bit more visual. So let's make our correlation matrix a little prettier. And we're going to do that using Seaborn's heat map. So we'll set it up in a variable. So core matrix equals df.core. Wonderful. And then we'll set up a figure and an ax using, plt.subplots. That's it. Fig size. I kind of know the fig size because I've seen this plot before. So I want it to be 15 width and height. And then we're going to go ax equals sns.heatmap. Would help if I typed map. And then we're going to pass it core matrix. And we want to annotate it, so we'll set a not to equal true. And we also want a line width. Line widths? Yeah, I believe that's it, of 0.5. And then what else do we need? There was a couple more things. Format equals, we only want 2 decimal places. So see here, these are like 6. So 2's going to be enough for us. And then CMap, to give it some nice colors, we'll go yellow, green, blue. Wonderful. Let's check it out. Invalid syntax. Oh, forgot the comma here. Classic. Wonderful. Okay, so what is this showing us? We've got some cut-off things here. That's that pesky matplotlib 3.1.1 error. But that's all right, we can fix it. So we might go bottom. You might not see that if you're using a later version of matplotlib than what I'm using at the moment. We need to adjust the y-axis limitations. So we'll go get y-lim. Wonderful. And then we're going to go ax.set-ylim. That's it. That's how we change it. We want to move the bottom up and we want to move the top down. Does that make sense? So bottom plus 0.5 and top minus 0.5. Does this work? Wonderful. That's looking a little bit better. It's not cut off. And this little adjustment here, this is from the research that I found by just searching for it. So matplotlib, Seaborn, first. I think that my history might have had it there. Matplotlib, there we go. First and last row cut off. And it's an example of searching for your problem when you have it. right? When you run into an issue, it's just about trying to figure it out. So they've got a similar problem to what we just had, cut off. And then come down here, you can find this is the lines of code that I'm using here. And in fact, they're making a correlation matrix as well. Beautiful. Yeah, unfortunately, Matplotlib 3.1.1 broke Seaborn heat maps. But that's all right. We've got our heat map. We've got our correlation matrix. Again, this is just the same version of this. A more visual format. I look at this and I understand this one a lot better than I do this one. So what is actually going on here? Well, we can see on the diagonal, we've got a lot of 1 values. But what this means, the diagonal is, we might zoom out 1 tick so we can see. The diagonal, this is giving a perfect correlation, which means the age column is exactly equal to the age column, which makes a whole bunch of sense, right? And the sex column is completely equal to the sex column. And so on and so on and so on, all the way down the diagonal here. But then we have a lot of other, actually, little cells here. We can see on the side, we got 0 up to 1. And some of them are positive, like this one here, and some of them are negative. We just compared chest pain type, which was CP, to our target. Let's investigate that. What's the correlation here? We got CP, it's got a positive correlation. So 0.43, remember the maximum value is 1. But this is telling us how chest pain is related to the target column. Well, if we're looking at this, and we did some research on a correlation matrix, I'm going to tell you because I've done this research myself. A higher positive value means a potential positive correlation. And a higher negative value means a potential negative correlation, or a decrease. What this is saying is as CP goes up, the target value also increases. Now, does that make sense? If we come up here, so if we look at this plot that we did before, so as CP goes up, the target value also increases. So remember our target value is 0 or 1, 0 for no disease, 1 for disease. Now, we're most interested here in the correlation because if you looked at this, no disease is highest at 0. So that means no disease, the target is 0, and chest pain type is also 0. Okay, so according to our correlation matrix, as CP goes up because it's a positive correlation, the target value should also go up. So let's investigate. Disease, this is the 1 value and this is 0. So blue is 1. Salmon is 0. Salmon, what a beautiful color. As our chest pain type goes up, 0, 1, 2, 3, does the blue column for 1 of target value go up? If we look here, it does go up slightly, and this drops off dramatically. And then it goes up here. It goes down here, but the ratio of disease to no disease is still much higher. So that's where the positive correlation comes from. It comes from chest pain type increasing, or our CP column. As that increases, our target column, meaning disease or no disease, also increases. So that's a positive correlation. That's why it's positive here. Now, let's have a look at one of the negative columns. So we've got a negative correlation here. It's about the same ratio, but just in the negative way. That means, if we look here, xang, we'll check our data dictionary for that in a second. As xang goes down, so should the target value. Let's not take this correlation matrix word for it. Let's reproduce this plot, except using the xang column. But before we do that, we might jump up here. What is xang? Exercise-induced angina. Now, if you're wondering what angina is, we've checked out that before. A condition marked by severe pain in the chest. So this means that if you exercise, do you get heart pain? And let's have a look. Exercise-induced angina, 1 equals yes, 0 equals no. So do you get heart pain when you exercise? If you do, that's a 1, and if you don't, that's a 0. There's a negative correlation according to our correlation matrix. I'm saying correlation a lot, I know. So xang compared to the target value, do they have disease or not, is negatively correlated. That means as xang goes down, the target should also go down. Now, there's only 2 values here for each of these, so this is actually a pretty straightforward example. So if we think about this, based off what you've heard about in terms of heart disease, if someone was telling you that when they exercise, they get chest pain, so they would have 1, would you predict closer to someone having heart disease or not? If they had exercise-induced chest pain, what would you be more inclined? Do they have heart disease or they don't? Well, for me, I would be more inclined to say, well, based off the rest of the data, if they're getting exercise-induced chest pain, there could be something going on with their heart, right? They could be heart disease. So this is where there's a negative correlation. This is where the negative correlation comes into play. Let's go down here, back to our correlation matrix. So there's a negative correlation of negative 0.44. So that means as xang goes down, the target value goes down. Based off what the core function is seeing in our data, exercise-induced angina, when I compare that column to the target column, I'm noticing that when xang is lower, so is the target column. Based off what we're looking here, and remember, it's only a 0.44 correlation. It's not a perfect 1, like -1 correlation. But just it's trending towards, if someone didn't have chest pain, so didn't have exercise-induced angina, the trend is negative, so it's trending towards them not having heart disease. Does that make sense? And you could go through all of these values. So this is pretty flat. Like this is almost basically 0. There's no correlation between FBS and the target. What's our data dictionary telling us? FBS. So fasting blood sugar. So this is saying, is the fasting blood sugar above 120 milligrams per deciliter? I believe that might be deciliter. 1 equals true, 0 equals false. So that's basically saying they're perfectly even. There's no real positive or negative correlation. It is what it is. And so that's the kind of insight that you can start to form with this correlation matrix. And that's the kind of insight that we want to sort of figure out on our own. If we weren't medical experts and we could only work with the data that we have, this is the purpose of EDA. This is the purpose of what we've gone through here, comparing different variables, looking at the distribution, comparing more different variables here. And this process, we could keep going with this, right? We could keep going until we really, really understand the data. But what we want to do next is model-driven EDA. So what that means is building a machine learning model to derive insights of how these independent variables here contribute to the target variable. Now, correlation matrix is one of them, but we're more interested in trying to predict for the future. The correlation matrix only deals with the data that we have. We're more interested in building a machine learning model that has predictive power based on the data that we have to predict on things in the future. So that's what we're going to look at next. If you're a little bit stuck here of what the correlation matrix is, don't worry. It's a pretty in-depth concept to understand, but where you can probably go next is by just searching what is a correlation matrix. So you go here, what is a correlation matrix? You could go to this first link. A correlation matrix is a table showing correlation coefficients between variables. Well, that sounds like a good resource. Start to read up on a little bit more. Hey, that looks a little bit like the graph that we made. But we've covered most of the crux of a correlation matrix. It's really just going, okay, looking at 2 variables and going, is the relationship positive, aka as one increases, so does the other? Or is the relationship negative? As one decreases, so does the other. But let's have a look at our workflow, see where we're up to. We've been through some data analysis. Now's time to get onto the machine learning in the modeling section. Let's see where we're up to here. If we look at our new project workflow, we've covered this. We've looked at some exploratory data analysis using NumPy, Pandas, and Matplotlib. Now's time to get into the machine learning part of things using Scikit-Learn. We'll start to test our little theories about what we found out in the exploratory data analysis. We'll start to see, does our machine learning model agree with what we found here, just exploring the data on our own? All right, I'm very excited. It's time to start modeling. It's time to start using machine learning to figure out whether or not we can classify whether someone has heart disease or not based on their health parameters. So in previous video, we said that we're going to try out 3 machine learning models. So we'll put them out here. We're going to try 3 different machine learning models. 1, logistic regression. 2, k nearest neighbors classifier. And 3, random forest classifier. And if you're wondering how we came about these 3, it's because we went through this diagram, the Scikit-Learn machine learning map. If we followed this through based on our data, we came across here. A good question you might be asking is, hey, I don't see logistic regression. We kind of covered that before where it said logistic regression, that doesn't really make sense. It's got regression here, so we're not trying to predict a number. We're trying to predict a category. Why are we using it for classification? And I was pretty stumped too when I found out that we could use logistic regression for classification. You might be thinking even further back, how did you even find logistic regression if it's not in here? Well, I was a bit confused at this too. I was wondering, why isn't logistic regression listed here? But after searching, if we go sklearn logistic regression, and you might be wondering, what if I didn't even know to search for sklearn logistic regression? Well, the way I stumbled upon this is I just went machine learning models used for classification problems. I searched something like that, and then someone suggested logistic regression. And so I decided to search logistic regression, and I found it in here, Scikit-Learn. It had an implementation. I could, of course, build it from scratch, but I'm more of a practitioner, right? I want to apply models that someone else has built in the past. So, and then I read through, and maybe it wasn't in this, logistic regression. Maybe it was in the user guide. That's, I think, where it was. So logistic regression, here we go. Despite its name, is a linear model for classification rather than regression. So this line here kind of clarifies the confusion in the name being logistic regression. And of course, you could read through all this. You got some math here of how it's actually implemented. But the reason why we're trying it is because we're pretending that we've tried linear SVC. We actually have in a previous Scikit-Learn video. We're going to say that it's not working. So now we're trying, we've gone through here, we're not working with text data. We're going to try k nearest neighbors classifier and ensemble classifier. So that's how we've deduced these 3 different models. And why logistic regression? Well, I've decided to throw it in here because it's not listed there. And we want to kind of check it out, because if it's not on the standard list of algorithms to try, we might try and figure it out anyway. And again, if this process seems like it's not really structured at all, it's like, where did Daniel find that machine learning model? What did he even think of? Again, it's just from searching something like this. Once we've defined that our problem is classification, if you're trying to figure out which machine learning model that you want to use, it's something as simple as this. And you could search for it and explore. And if we go back to our keynote here, that's what we're doing. We're up to experiments. We're trying different machine learning models. But that's enough talking. Actually, one more thing. And that's what I want to try and encourage you to do, right? Is that because there's so many different ways to do things in machine learning, a lot of it is about just searching for the answer, or not even the answer, just asking questions and trying to implement them. That's what we're going to do now. So, because we want to build 3 different models, and because we want to evaluate them, and because we want to do a couple of experiments to see which one is the best, we want to train them on the training data and test them on the test data, evaluate them. What we might do is set up a little dictionary with our models in it, and then we'll create a function to fit and score our models. So rather than rewrite all the same code for fitting and evaluating our models, we'll set it up in a function. Yeah, that's a good idea, Daniel. Let's do that. All right. So put models in a dictionary. We're going to go models equals logistic regression. And we're going to go here. And this is logistic regression. And then we want to go KNN. We're going to instantiate the class here. So it's going to be K neighbors. We can probably press tab autocomplete, let's be real. And then we're going to go here, random forest. And this is going to be our trusty random forest classifier. Beautiful. And then let's go create a function. We want to fit and score the model. So we want to train it. We need a function to train our models on the training data and then evaluate them on the test data to fit and score models. So def, fit and score, something simple. It'll need to take our dictionary of models, and then we'll take xtrain, xtest, ytrain, ytest. And we could put a little doc string here just to make sure our code is legible. If someone else was to use this function, what would it do? So fits and evaluates given machine learning models. And then we'll tell it what parameters we're using. So models, a dict of different Scikit-Learn machine learning models. What's xtrain? We know what xtrain is. Training data, no labels. Xtest is testing data, no labels. And then ytrain is training labels. And then ytest is test labels. Beautiful. And now what should we do? We might set a random seed. Set random seed even if it's within the function to make sure that our results are reproducible. And then we're going to go here. We'll make a list to keep model scores. Or actually, this is probably better. Make a dictionary. That's what we want because we're working with dictionaries here. We want to go model scores equals an empty dictionary because we're going to fill it up in a second. We'll talk through this function as we do it. So loop through models. So this is where we're going to go for name model. So name is the key. Model is the value of our dictionary. So for key value in models.items. So we're accessing the items of a dictionary with .items. And then we're going to go fit the model to the data. This is where we go model.fit xtrain ytrain. So we're fitting our model there. So for each model, it's going to fit it to the training data. And then we want to evaluate the model and append its score to model scores. So this is how we're going to evaluate each model in one hit. We're going to save the name of it to our dictionary here as the key, and then its score as the value in model scores. So model scores name. So we're creating a key in the model scores empty dictionary, and then we're going to go equals model.score. So this is our model here. So for example, if it was logistic regression, we've just fit it. So logistic regression.fit xtrain ytrain, and now we're appending logistic regression.score xtest ytest to model scores under the name logistic regression. And if we're going through that and you're thinking, whoa, that's a fair few steps, it's only about 2 or 3, but that's all right. When I first worked with these kind of functions, I was like, hold on, I'm used to just doing this line by line. But we're being efficient in this project. So we're going to return model scores, which will return a dictionary. So we'll hit Shift and Enter. And I wonder if this will work. So basically what it's going to do is it's going to take our dictionary of models. It's going to set up a random seed. It'll set up an empty dictionary. Then it's going to loop through our models dictionary. So for name model, so for logistic regression in models.items, logistic regression, we'll pretend it's logistic regression, .fit, so telling the logistic regression model to find the patterns in the training data. And then it's going to create a key in our empty dictionary model scores with the score of how well our logistic regression model performs on the test data, aka using the patterns that it's found in the training data. And then it's going to return our model scores dictionary. And then we're going to see how each of our model performs on the test data set. And our 3 models here, we should have 3 different scores. So we're going to leave it on a cliffhanger there, and we're going to evaluate our 3 models in the next video. So I'll see you there. Ooh, I'm rubbing my hands if you can hear that. You know why? Because I'm pumped. I'm ready to evaluate our machine learning models, or see how they go. See how each of these models, using the function we've just created in the last video, see how logistic regression goes, k-nearest neighbors classifier, and random forest classifier goes at finding patterns in our training data, and then how those patterns get evaluated in our test data. So without any further ado, let's see how each of these models performs. So we can call our function fit and score, and hopefully it works. And we got here, we see that it takes models, or actually if we press Shift Tab, this is where our docstring comes in handy because it tells us what happens. Fits and evaluates given machine learning models. This is beautiful. This is just like what we've seen with other functions, but except we've created this one ourselves. That's the helpfulness of a docstring, right? So we're going to go here, models equals models, which is our dictionary of machine learning models. We could just go xtrain, xtest, but for completeness, we're going to go xtrain equals xtrain, and then we're going to go xtest equals xtest, and then we're going to go ytrain equals ytrain, and then finally ytest equals ytest. And if we've written a function correctly, what do you think it's going to return? I'll give you a few seconds. Okay, that's enough because we want to see it. If in doubt, run the code. So let's see what our function returns. Okay, so we get some warnings here. What does it say? Stop. Total number of iterations reached. That would require us to dive in. Increase the number of iterations. So this is where it's helpful. Increase the number of iterations, max iter, or scale it down. So this is saying that potentially our logistic regression model could be improved. And to figure out how you could do that, it would require going to the documentation for alternative solver options. But what we're going to do is just work with what we've got so far. So if we have a look at this, this is the score, how each of our models, without tuning, oh, that's a spoiler for what's coming up. This is how each of our models, as the baseline class, has performed on finding patterns in our test data. So it's getting the score here. This is what we're getting back. So if we look at this, which one's the highest? Look at that. Logistic regression coming in as the dark horse, not even on the machine learning map, right? And it's getting the highest score. Well, this might take a little bit of investigation because remember, where are we up to? We're up to experiments, and that's what we're doing here. An experiment is comparing different models, trying different models and comparing them to each other. Now, this is a comparison in a dictionary, but if we wanted to show this to someone, we might compare it visually. So let's do that nice and quickly. We can make a model. Actually, we might make a little heading here. So we go here, model, comparison. Beautiful. So model compare equals, we might turn our dictionary into a data frame because that's nice and simple. So model scores. This is just taking this dictionary here, model scores. And we're going to set the index to be, what does it have to be? It has to be a list called accuracy because that's what this score function here, because our models are all classifiers, their default score metric is accuracy. We saw that in their Scikit-Learn section. So if we go here, model.compare, we need to transpose it, plot.bar, boom. Now, I'll just show you why we need to transpose it, because if we did that, it would look weird like that, and we actually want it to look good like that. So this is quickly showing how accurate each of our different models are. And you can see logistic regression just tips out our random forest. And KNN, well, because that's nowhere near the accuracy of our logistic regression model, we're going to say goodbye to KNN. So once we've got this graph, this might be something that we can take to the boss or one of our colleagues and say, hey, look at this. We've built a machine learning model, a beautiful logistic regression model, and it's performed the best. So we're going to use the logistic regression model in practice. And so you might go, I found it. And your boss is like, nice one. What did you find? And then you're like, well, the best algorithm for predicting heart disease is logistic regression. And then she might say something like, excellent. I'm surprised the hyperparameter tuning isn't finished by now. And then you might wonder, what is hyperparameter tuning? Yeah, me too. It went pretty quick. So you're sort of covering yourself here. And then she might say, well, I'm very proud. How about you put together a classification report to show the team and be sure to include a confusion matrix and the cross-validated precision, recall, and F1 scores. I'd also be curious to see what features are most important. Oh, and don't forget to include an ROC curve. And then you might be thinking or asking yourself, okay, there's a lot of complex words there. Great. But then you actually say, of course, I'll have it to you by tomorrow. Don't worry, we're going to take care of all these things. We're going to take care of all these things in the next video. Because we're still at a point where, even though we found a great machine learning model, and we've probably shown it to the boss or one of our colleagues, and they've gone, wow, logistic regression performing at 88% accuracy, we're still not near our valuation metric, which is if we come back up the top, which as we said, we kind of want at least 95% accuracy to continue with this experiment. So that's what we're going to be doing, as well as fulfilling all those requests that the boss asked us, just to make sure our model is a little bit more robust than just getting the default score metric. So without any further ado, take a little break, have a review of what we've done so far, and we're going to review some of the things that we need to make sure we do to make sure our classification models are evaluated correctly and are improved as well as possible. Alrighty, so we found a logistic regression model that performs pretty well, but we went and showed that to our boss, and then she said we had to find a whole bunch of things like hyperparameter tuning, feature importance, confusion matrix, cross-validation, and these things could sound made up to someone who's not a budding data scientist or machine learning engineer like yourself. But being the budding machine learning engineer and data scientist that you are, you know that data scientists make up words all the time. And the good thing is that these aren't made up. These are things that we can actually find. So now we've got a baseline model, and we know a model's first predictions aren't always what we should base our next steps off. What should we do? If we remind ourselves of the classification metrics and regression metrics, we're not worried about regression, right? Because we're working on a classification problem. We've used the default accuracy. And then there's precision, there's recall, and there's F1, which are all part of the things that the boss asked us. And we got a confusion matrix. Okay, we should probably make one of them since we're working on a classification problem. Then we got a classification report, which has a bunch of information here like precision, recall, F1 score, support, accuracy, macro, average. Far out. And then we got hyperparameter tuning. We've covered before, but we've got a lot of steps. So first, we should put down what we're going to tackle. Let's look at the following. Because we're a part of the experimental phase, that's what we're going to be working towards. We're going to be taking our models that we've got, these are our baseline models here, and we're going to be experimenting with them further, seeing if we can improve them and seeing, does logistic regression perform best on accuracy, or could a tuned or hyperparameter tuned version of a random forest beat it out, or maybe KNN could improve. Who knows? Let's write down a list. Let's look at the following. Hyperparameter tuning, feature importance, confusion matrix, cross-validation, precision, recall, F1 score, classification report, ROC curve, area under the curve. So as we saw in the Scikit-Learn section, these are some of the things that you should pay attention to when you're working on a classification model. These two here are actually part of almost any machine learning model that you'll be working on, but these are specific to classification. We've seen the difference between regression and classification metrics, but since we're focusing on the classification problem, whether or not someone has heart disease based on their health parameters, we're going to be focused on looking at these. So let's jump into it. So the first things first, why don't we try hyperparameter tuning and cross-validation? And remember, what's hyperparameter tuning? Well, to cook your favorite dish, you know that to set the oven to 180 degrees and turn the grill on. But when your roommate cooks their favorite dish, they set the oven to 200 degrees and use the fan force mode. Same oven, different settings, different outcomes. This is the same for machine learning algorithms. You can use the same algorithms, but change the settings, aka hyperparameters, and get different results. But just like turning up the oven too high, if you do that for machine learning algorithms, you tweak the settings too much, you can change the settings and it works well, or so well that it overfits. So we're really here, what we're doing to do is look for the Goldilocks model, one which does well in our dataset, but also performs well on unseen examples. Should we tune a k-neighbors classifier? Yeah, we might do that. Even though we've said goodbye to the KNN classifier, we might just see how would you tune it. And if you're wondering where I would start if I was trying to approach this, this is what I'd start with. How to tune a k-neighbors classifier model. We go here, in-depth parameter tuning for KNN, model selection, tuning and evaluation in k-nearest neighbors. So if we were to read through these, we would probably find some information that we're going to cover here. So let's start it out. Let's make a little heading here. We'll go here, hyperparameter tuning. Let's tune KNN. Let's go a list of training scores, an empty list. So train scores, and then a list of test scores, empty list. Because what we want to do is compare different versions of the same model, so model with different settings, and compare their scores on the two different data sets. Looking up what we looked up before, if we were to read into these, again, you can do this with almost any machine learning model, or basically, yeah, any machine learning model. This is a part of the research. This is a part of the experimentation step of many machine learning problems, is searching up things like this, then reading what you can find and bringing it back to a scenario like what we're doing here. But let's just pretend we've gone through that. So we're going to create a list of different values for n neighbors. Now, why n neighbors? Because, as I said before, when we did our reading, we found that if we go sklearn knn k-neighbors classifier, we see that n neighbors is one of the parameters. And we could see this by reading through the documentation of Scikit-Learn as well. And so the number of neighbors used by default for k-neighbors queries. In our research on how to tune a KNN model, we found that we can adjust the number of neighbors. And if you want to find out more about this, you can check out the documentation. You can read it up here. So that's what we're going to do. We're going to create a list of different values. So the default here is 5. So maybe what we might do is try different values from 1 to 20 or something like that. So let's see here, neighbors equals range 1 to 21. Wonderful. And then we're going to set up KNN instance. So we'll go maybe KNN equals, what is it? We know this. K-neighbors classifier. Beautiful. And then we might go loop through. We need to loop through different n neighbors, which is our list that we made here. For I in neighbors, I'm thinking out loud here, we'll go knn.set params. Remember, you can adjust the parameters of a machine learning model in Scikit-Learn using .set params equals I, because I is going to loop through this range here. Wonderful. And then we're going to fit the algorithm. What we're trying to do here is improve on this baseline score. So this is with the default of 5. And so we're going to try 20 different versions, 1 to 20, to see if it's any better. Oh, that didn't do anything. I accidentally hit Shift Enter. I'm trigger happy, you know. My fingers are they just default to Shift and Enter whenever they want. Now we want to update training scores list. So we're going to go training. We want train scores up here. train scores.append. Now we want our KNN instance.score on xtrain, ytrain. Wonderful. And then we want to update the test scores list. And we'll do that test scores.append knn.score. And you can probably guess that this is going to be on the test set. Beautiful. Bonus points if you did. Now, what this is going to do is just going to loop through this range of 1 to 20. And then it's going to create 20 different KNN models and append their scores to lists. So let's check out those lists. Train scores, Shift Enter, wonderful. And then go test scores. Yep, typo. Okay. Now we've got 20 different scores or so, but these are probably best visualized. Let's see how we would do that. Let's go plt.plot. We'll go neighbors, and we'll go train scores, and then we'll go label equals train score, of course, yes. PLT will add another plot, neighbors, test scores, label equals test score, wonderful. And we want to go PLT, actually let's just see what this looks like, X label, we'll go number of neighbors, because that's what's on the X. I'm spelling neighbors the Australian way here with the U there. Or maybe it's not Australian, maybe it's just a different version. But neighbors in Scikit-Learn is spelled with no U. So this is the X, and then plt.y label is going to be the scores. So this is X, Y. So this is going to be model score. And then we want plt.legend. And we'll see what comes up. Actually, we might, a little tidbit here, max F, so maximum KNN score on the test data. We're going to go max test scores, it's going to be accuracy, so we want times 100.2F, close parentheses, and then close string. That should work. Wonderful. Okay, so we can see here that we're really paying attention to this test score here. So we get the highest value here is around about 11 for k nearest neighbors. So if we look at the graph, actually let's adjust these xticks so we can see where it actually is. xticks.np arrange 1 to 21 space of 1. So what this is going to do is just bring out a list of range of 1 to 21 of space 1, which is the exact same as what we're using here. So neighbors equals range 1 to 21. So let's do that. And yes, our assumption before we adjusted the xticks, which is these just little labels down here, was that a KNN, or an N neighbors value of 11, yields the best score on our test data set. So if we come up here, the default we remember is 5. So we've just done a little bit of hyperparameter tuning, and we were able to improve our KNN classifier's results on the test data set by changing it from the default 5 and N neighbors parameter. So we're doing hyperparameter tuning here. Change that to 11, and we get 75.41 versus our initial result, which is back up here, of 68%. Well, even then, even after improving it to 75 or whatever it was, it's still far below our logistic regression and random forest. So I think this has put the nail in the coffin for our KNN model, is that because even with a hyperparameter tuning, it still hasn't reached the scores that we got with logistic regression or random forest. And so because of this, we're going to discard KNN for now. This is part of our experiment. A big part of experimenting in machine learning, step 6, is going through different machine learning models and figuring out which work and which don't. So what we're trying to do here is, as quickly as possible, work through different little experiments like what we've just done tuning KNN and seeing which model performs best on our data. So what we might try and do is we've tuned KNN by hand. Like we wrote out this little for loop here. That was a bit tedious, right? So if you had to do that for every single machine learning model, you might run into some problems. It was okay here because we had one parameter tuned, but if you had more parameters, writing these for loops is going to be very inefficient. So what we might do next is see how we can tune logistic regression and random forest classifier using randomized search, CV, which stands for cross-validation. So instead of us having to manually try tuning different hyperparameters by hand, randomized search CV, which we've seen in the Scikit-Learn section, it's going to try a number of different combinations of hyperparameters for us and evaluate which ones are the best and then save them for us. So that's what we're going to have a look at that in the next video. Welcome back. In the last video, we saw how to tune one of our machine learning models, specifically the k nearest neighbors classifier, by hand. Now this is hyperparameter tuning. What I've done is I've just adjusted this little title here to say hyperparameter tuning by hand. But as you could imagine, if you had more than one parameter or hyperparameter, in our case, we only tuned n neighbors. We go up to the k neighbors classifier. We only tuned this one parameter. If we wanted to tune all of these, they could get a bit tedious. We'd be writing for loops for days. So what we're going to do here is, and remember we've also written off our k nearest neighbors, we're in the search of better results. So because our logistic regression and random forest classifier are performing better, we're going to cut the k nearest neighbors model out of our experimentation. So now we're going to go hyperparameter tuning with randomized search CV. And so this is what we saw in the Scikit-Learn section. And if we search it up, randomized search CV sklearn, we'd find it here. Beautiful. So there's the documentation there. You can read through that on your own time, but we're going to see it implemented. And again, if you're wondering how you could find the hyperparameters to tune a certain machine learning model, well, here's what I would do for logistic regression. So how to tune a logistic regression machine learning model in Python. Something like that. If we search that up, logistic regression model tuning with Scikit-Learn, beautiful. Logistic regression using Python, Scikit-Learn, hyperparameter optimization and machine learning models, tuning parameters for logistic regression. If we were to go through these and research it, do our own experiments and figure out things and ask more questions, you'd probably find some pretty good answers. But for now, we're going to pretend we've gone through those steps and we've figured out that we can use randomized search CV and that we can tune a bunch of different parameters. Let's do that. We're going to tune logistic regression, our logistic regression model, which is that, and random forest classifier. Using randomized search CV. And again, if you need information about which parameters you can use for logistic regression, I've even spelled that wrong. Typical Daniel. Logistic regression and random forest classifier, you can go up here, sklearn logistic regression. So if we look in here, this is going to give us a list of different parameters, and you might read the documentation. And trust me, I did this. The first time I did this, I read the documentation and I'm like, this means all of these terms like elastic net, L2 penalties, bool. Actually, I know what bool means. True or false, right? All these things didn't mean much to me. It was only once I started to do some research and go through and figure out what all these different parameters actually meant was that I started to understand it. And the same goes for the random forest classifier. You could do the same thing. Put that into the sklearn documentation, or change this to be how to tune a random forest machine learning model in Python. These are steps that people like machine learning engineers and data scientists take every single day to figure out how to improve their models. No one in the beginning knows how to do this off by heart. Even after doing it many times, I still have to look these things up. So we go here. Let's see how we would do it. So the first thing to do with randomized search CV is, and if you're wondering what CV stands for, it stands for cross-validation. We saw that in Scikit-Learn. And more specifically, cross-validation, what it does is instead of doing a normal train and test split like we've done before by creating one training split and a test split, aka 80% in the training split and 20% in the test split, it creates, this should really be K, but I've done 5 because it looks nice here. This can be k-fold cross-validation. So 5 is the default in Scikit-Learn in the latest version, but you can really adjust this. And what it's going to do is it's going to create 5 different versions of training data and 5 different versions of the test data, and then evaluate different parameters. Remember, because we're doing hyperparameter search, evaluate different hyperparameters on all of these different sets of all of these versions of the training and test data, and work out which set of parameters or hyperparameters is best across these 5 different splits, rather than just being one single split. So if we go here, let's do it. So what we need to do is create a hyperparameter grid for logistic regression, and reading the logistic regression documentation, as well as searching up here for logistic regression, we figure out that there's a few hyperparameters that we can tune, such as the value for C, which if we look in here, if we go down here, C. So inverse of regularization strength must be a positive float. Like, again, you could read this the first time in the documentation and go, what do any of these words mean? That's why it requires research to check it out. And then there's another one called solver. So we'll go here. We'll just have a look at what a parameter grid looks like. C. And again, there are more. We're only using 2 here. So we're only using C and solver. You might find in your research that you could adjust the penalty, you could adjust the fit intercept, you could adjust a whole bunch of hyperparameters. But the overall concept of adjusting hyperparameters is what we're focused on. So we're going to set this. After our research, we know that a good value is NP log space, -4. And if you're wondering what the log space, because I'm kind of throwing these things out relatively quickly, log space does, if we go here, returns numbers spaced evenly along a log scale. So the start, stop, number. So this is going to be between -4, between 4 and 50 of them. And if you're wondering what a log space is, these are the ways you can do it. Let's go, what is a log space? Log space reduction, L complexity. Can you explain in simple words what is log space reduction? So we could read that. Again, fair few complex words there, but after a little bit of effort, you'll be able to figure it out. So we go here. We're going to only really use one solver here because really after the research and finding what hyperparameters we should adjust, we find that C is probably the most valuable one for logistic regression. So we're only going to use one value for solver. So really what we're testing here, we're creating a grid of numbers on a log space between -4 and 4. So there we go. Oh, sorry, because it's a log space, it's 1 times 10 to the power of -4 up to 1 times 10 to the power of 4. So a pretty big space there. These numbers are pretty well separated. So let's get rid of that. And now we'll create hyperparameter grid for random forest classifier. Wonderful. And through our research, we find that some of the best parameters for a random forest are number of estimators, which is, if we're using a random forest, and estimators is how many trees that we have in our forest. So NP arrange. And you might be wondering why I'm using ranges here when I'm going through this. Well, the reason is because if we look up the documentation, I know in a previous video we haven't explicitly used range, we've used a list. Just for a refresher on what a range does, let's check out this. So it's basically just going to create a range of numbers, space 50 apart, because of 50 here, between 10 and 1000. So if we look up randomized, I think we already have it. Maybe here, there we go. There's somewhere here. In contrast, we go, it is highly recommended to use continuous distributions for continuous parameters. So that's why we create a range of different values. This is where we read that from. Rather than just being an explicit list, we're creating a range of continuous distribution for our hyperparameters for randomized search CV. But that's just in the documentation. So we go here, you could still just use a list. But the documentation of people who have written the Scikit-Learn library recommend us to use a range of values. So we're going to go max depth here, which is another one that we found through our own research of a hyperparameter that we can tune. Remember, for any machine learning model, a quick search of going, hey, I'm using this model, I've figured it out, I followed the scikit-learn. I don't have the map, do I? Yeah, we do. I followed the map and I've decided I'm going to use a random forest classifier. How can I do hyperparameter tuning of it? Well, that's where it comes to searching something like this, right? So we'll go here, we find that another one is the min samples split. And then we go here, and we'll use a range actually. I've said that we're going to use a distribution, but here, max depth, we haven't used a distribution, we've just used an explicit list. But we'll use another range here, and then we'll go here, and we'll also use min samples leaf, np, a range, 122. Beautiful. So now we have two hyperparameter grids for the two models that we're going to try and hyperparameter tune using randomized search CV. So what we'll probably do is we'll end this video here and then we'll come back and we'll use these two grids along with randomized search CV to try and improve our results of our logistic regression model and our random forest classifier beyond what we initially got. So beyond these initial values that we got. And remember, these values were obtained without using cross-validation because we only used a single train and test split. Whereas, if we go into Keynote, in cross-validation, so this is what we used to get our original scores, a single train and test split. Whereas in cross-validation, we're going to be using multiple train and test split. Remember in the scikit-learn section, we discussed that if you're going to provide a metric in terms of how a model is performing, it's probably best to use a cross-validation metric, especially with classification problems. So let's revisit that in the next video of tuning our random forest and logistic regression with randomized search CV. Wonderful. So now we have hyperparameter grids for our logistic regression model as well as our random forest classifier. Let's tune each of them using randomized search CV. So now we've got, just repeat what we just said, got hyperparameter grids set up for each of our models. Let's tune them using randomized search CV. We'll change that into Markdown. Wonderful. So first up, we'll go tune logistic regression. Now at the moment, our logistic regression model, if you scroll back up, is getting the best results just on a single train and test split. But let's see if those results carry through to a cross-validation split, which is what randomized search CV is going to help us with. So tune logistic regression, we'll set up a random seed so that our results are reproducible. And then we're going to go set up random hyperparameter search for logistic regression. So RS for random search, log reg for logistic regression, and that's this log reg grid. That's short for logistic regression. That's short for random forest up here. We're going to go randomized search CV, logistic regression. Wonderful. And then we're going to go param distribution, which is equal to our log reg grid. And we're going to use a cross-validation of 5, which is similar to what we've seen here. So 5-fold cross-validation. You could use 10-fold, you could use 20-fold. What you should know is that the higher this number, the longer it's going to take. So, because it has to build a model for each and every single set. So 5 is generally a pretty good value to use. Again, you might want to test that experimentally depending on the size of your data. Number of iters equals 20. So that means an iter means we're going to try 20 different combinations, which I think will be every single one of them because we've only got 20 different values for C here, but that's okay. So we're going to go then verbose equals true, which just means it's going to output a few things for us. Now with that, we can go fit random hyperparameter search model for logistic regression. So what this is going to do is call randomized search CV. It's going to cross-validate a logistic regression model 5 times for 20 iterations. So we should have about 100 or so examples, 100 or so different tests. 5 times 20 is 100. We're going to fit this on the training data. Wonderful. Oh no. Param distribution. Oh, shons. There we go. Fitting 5 models for each of the 20 candidates, totaling 100 fits. Wow, and that's done. You see, oh well, it's zoomed in here, so you can't really see. It's going to tell us what the parameters are that it's used. You see here, we can see param distributions. C is all these different values here. Solver is lib linear. Let's zoom back in because it's easier to see. And now, we can check the best parameters by going rs log reg dot best params is solver lib linear, that makes sense, and the C value is 0.233. Wonderful. And so now let's evaluate log reg dot score on our test data. 88.5 accuracy. So if we go back up here, did we beat our original result? 88.5. No, we got equal to it. The logistic regression model out of the box must be pretty good. Because we've only tuned 2 hyperparameters, you could look up more different values that we could tune. But we're going to leave that here for the time being. We're going to see what it's like to tune our random forest classifier. So we'll put in a little commentary here. So now we've tuned logistic regression. Let's do the same for random forest classifier. Markdown, wonderful. And we're going to do the same thing again. Set up random seed. Now we could just copy the code from here and just change the variables. We're in the habit of writing it out, you know. Dot random seed, we're going to set that to 42, our favorite number. So set up random hyperparameter search for random forest classifier. Wonderful. We're going to go rsrf equals randomized search CV. Wonderful. We're going to put in our random forest classifier. And then we're going to pass it param. We'll just use tab autocomplete, so we're not doing typos here, Daniel. Come on. Like we did before. So we're going to pass it the RF grid, which is the random forest grid. So our hyperparameter grid up here. So we'll come down here. What's next? CV, we're going to set that to 5, so 5-fold cross-validation. Number of iterations is going to be 20 again, so we're going to try 20 different combinations of these hyperparameters. Now, if we were to add these all up, so this is 50 times 4, 200 times 2, or actually, yeah, times the space between here. So this is going to be a lot more. Let's just leave it at that. There's going to be a lot more different combinations, but we're only going to try 20 of them. So randomly try 20 of them. So verbose equals true. Then we go fit random hyperparameter search model for random forest classifier. Wonderful. And we'll go RS RF, which stands for random search, random forest. Fit. We'll do it on the training data. Ytrain. Wonderful. What's happened here? We've got something wrong again. Invalid parameter. Mid samples lead. A typo. The classic. Min samples lead. I hope you noticed that when I was going through. It's alright if you didn't, because I didn't notice it either. Now we'll run this. So this should work. This might actually take a little while. Hope not. If it does, I'll pause the video and we'll come back when it's finished. Well, we just finished up, so that took about a minute or so on my computer. It'll also depend on how fast your computer's processing speed is how fast it goes through this sort of process. It does have to build 100 different models. So let's check it out. Now that it's finished, how can we find the best parameters of our random forest random search model? You might already know this, because we just did it with the logistic regression. It's okay if you don't. Find the best parameters. This takes a little bit of practice. Find the best hyperparameters. I'll give you a second to think of it. Hint, it's in an attribute. It's in an attribute of this one here. All right. Let's figure it out. So we're going to call the best params attribute. And so this is going to show us our best parameters. So number of estimators, the best results were 210. The best min sample split was 4. The best min samples leaf was 19. And the best maximum depth was 3. Remember, that was only 20 different models. So 20 candidates. We could increase this to 100 or something. That would take a little bit longer. But in our case, 20 is enough. We're focusing on the principle here. We could revisit this in a second to try and improve our results, but what we're trying to do here is just minimize our time between experiments. So let's figure out how our random search, random forest model went. So evaluate the randomized search, random forest classifier model. So RS, RF score, X test, Y test. How did it do? 86.88. Let's go back up here. How did it perform versus our original scores? Oh, we got a little bit of an improvement. Yes. So this is our initial random forest model. 83.6 accuracy, because remember if you times that by 100. But even though we've gone up a little bit, we've gone up a few percentage points to 86.8, we can check out the original one here, model scores. Our logistic regression model is still, our default one is still better than the random forest, than the tuned random forest. Now, of course, we might be able to try different search, different hyperparameter combinations to try and push our random forest model further. But what we might do is, because we're trying to minimize our time between experiments, we might push on with our logistic regression model. So now, you see how we're going through this process of elimination? Trying to figure out which model works best for us, which doesn't work, and then just slightly incrementing on the one that performs the best. That's where we're up to now. We're well and truly in the experimentation phase of this 6-step framework. We're trying out different models, we're trying out different hyperparameters. So now we've searched better hyperparameters for our logistic regression model back up here using randomized search CV. What we might do now is use grid search CV, which exhaustively searches through hyperparameters. Rather than randomly looking at different combinations of hyperparameters, as we saw in the Scikit-Learn section, grid search CV, and you can look up the documentation for this, sklearn grid search CV. Grid search CV searches an exhaustive search over specified parameter values for an estimator. So that's what we might do now with our logistic regression model. There's a couple of steps for hyperparameter tuning. 1, you could go by hand. 2, randomized search CV. 3, grid search to really narrow things down. That's the process we're following now. We eliminated K and N with tuning hyperparameters by hand. We eliminated our random forest model. Again, we could always revisit these things. This is part of the experimentation using randomized search CV because our logistic regression model is performing better than our randomized search random forest model. So now we're going to use grid search CV with our logistic regression model. So have a little review of what we've done. See if you could try different hyperparameter grid for each of our logistic regression and random forest in our randomized search CV. See if you can try some different parameters. Maybe you increase the number of iterations. See if you can push those results a little bit. But for now, in the next video, we're going to focus on tuning our logistic regression model using grid search CV. All right, let's see how we can tune the hyperparameters of our logistic regression model using grid search CV. So grid search CV. Beautiful. And if we put a little note here, since our logistic regression model, now remember, it's quite confusing. I still look at this and think it's a regression model. This is a classification model. Provides the best scores so far. We'll try and improve them again using grid search CV. So if you want to look up the documentation for grid search CV, it's in Scikit-Learn. You can just search Scikit-Learn grid search CV, and you'll see it's an exhaustive search over specified parameter values for an estimator. So what we might do is just recreate different hyperparameter grid. So different hyperparameters for our logistic. And again, if you want to find the different hyperparameters you can choose for a machine learning model, in our case it's logistic regression, you could search something up like this. So how to tune a logistic regression machine learning model in Python. That's where we found things like what we're going to create here. So log reg grid, we've made this up here before, but we're just going to bring it down so we've got it in our line of sight. Log reg grid. So we'll just basically put in the exact same thing. So C equals np.log space -4 for 20 different spots. Actually, we might, just for fun, you know, we're going to increase this to 30. Because we're using grid search, why not? Why not live on the edge, you know? Create different hyperparameter spaces that we haven't seen before. That's what life is, exploring things we haven't tried before. That's where all the fun is. So we'll go setup, grid hyperparameter, search for logistic regression. We'll go gs log reg equals grid search CV. That needs a little capital there. Maybe we'll use tab autocomplete for this, just because we're keyboard ninjas here. Now, the difference between randomized search CV and grid search CV is this little hyperparameter here. In grid search CV, it's just called param grid. In randomized search CV, it's called param distributions. So then we'll pass it this. Our new log reg grid, which has 30 intervals between -4 and 4 on a log space, because we are living dangerously here. And CV equals 5, and then we're going to go verbose equals true, just to put out our little outputs of what's happening. Now you'll notice there is no n-iter here, unlike in randomized search CV. There's n-iter because grid search CV tries every single combination of parameter in here and finds the best one. So we want to go fit. We've saved this, by the way, our logistic regression grid search to gs log reg. For gs is for grid search. So fit our grid hyperparameter search model, wonderful, gs log reg dot fit x train y train, and then we go boom, run. This is going to fit 5 candidates because totaling 150 fits over 30 different sets of hyperparameters, because we have set CV equal to 5, and it's done already because logistic regression is nice and fast. And so check the best hyperparameters and go gs log reg dot best params. Wonderful. Okay, so we've got a C value of that, really long number. Solver is live linear. Well, we kind of guessed that because there's only one option there. How can we evaluate this? We want to evaluate the grid search logistic regression model. So we'll use our test set again. So gs log reg dot score on our test data, x test, y test, and let's see. 88.5. Did we get any better? Come back up here. So if we look at our randomized search log reg, we got 88.5 as well. Are the later decimals different? No. They're the exact same. Well, it looks like our randomized search and our subsequently, I think our baseline logistic regression model got that same score. Subsequently, the logistic regression model has done very well. That's pretty good for a model that doesn't appear in this classification map. So Scikit-Learn, I think you guys need to put logistic regression in here, because otherwise people are going to be missing out on it. So that's something to keep in mind, right? Is that although you find these maps and these cheat sheets online, it still helps to do your own research and not just rely on this handful of stuff that's going on here. Because remember, we know how broad machine learning is. Like, just look at this. There's just a lot going on here, but even within these little bubbles themselves, there's still more that can be done. So that's, I can't stress enough how important it is to try your own research. Okay, so now we've tuned our logistic regression model using grid search. We get the same results as before, even with increasing the number of different parameters that our logistic regression model was searching over. What we're going to do now is probably stick with this logistic regression model. We could spend a little while on this hyperparameter tuning, like going through different resources here, like this one here, hyperparameter tuning. We may be able to squeeze out another % or a couple of % of accuracy, But for now, we've got a few requests from our boss. Remember, she was telling us earlier, we need to have a look at the following. Hyperparameter tuning, feature importance. What's that? Okay, well, we've done hyperparameter tuning. We've figured out logistic regression is probably the model we're going to stick with for now. We got a confusion matrix. We've done a bit of cross-validation through randomized search CV and grid search CV. We need precision, recall, F1 score, classification report, ROC curve, area under the curve. My goodness. All right. Well, let's do it. So that's probably what we're going to do over the next few videos is use our grid search logistic regression, use our logistic regression model with its best hyperparameters that we found using grid search to get the things like the ROC curve, the confusion matrix, the classification report, the precision, the recall, the F1 score, and all those other classification goodies that you should use with every classification model. So maybe you want to try a few different parameters with grid search by searching up something like this. That can be a little extension, but otherwise we'll move on to the things that our boss is asking for us to make sure that we're reporting our results and our classification models correctly. Now we've tuned the hyperparameters of our logistic regression model and it's getting pretty good score here. But remember this score, the default score for a classifier is accuracy. What we want to do now is create some evaluation metrics around our model that go a little bit beyond accuracy. More specifically, let's create our tuned machine learning model. Actually, machine learning classifier is probably a better one because these evaluation metrics are specific to classification. So we're going to go beyond accuracy. So here, more specifically, we want an ROC curve and AUC score. We also want a confusion matrix. I'm putting 4s in there. That actually looked like it was from the matrix with lots of numbers. You know, that flowing green screen. We want a classification report. What else do we want? We want precision, recall, and F1 score. And it would be great if cross-validation was used where possible. So let's turn that into Markdown. So this is what we're going to be working on. We'll use our tuned grid search logistic regression model as well as the best hyperparameters for it. And we'll see where they come into play in a second. So first of all, when we evaluate a model, it's always comparing how a trained model's predictions compare to the truth labels. So what we have to do is make some predictions first so we can compare them to the truth labels, aka the labels in the y-test dataset. So let's do that. We'll write a note here. To make comparisons and evaluate our trained model, first we need to make predictions. So what we'll do, we'll go make predictions with tuned model, and there's a beautiful function called predict that we can use for that. So we'll save it to ypreds, and we'll use gs logreg, which is just our trained version of our grid search model. So gs logreg dot predict, and we're going to predict on the test data. Ypreds, wonderful, and let's see them just to make sure we're not going crazy. Beautiful, and now we need to compare them to the test data set. So we have a look at this here. Okay, so if we wanted to go 0, 0, we can know it's got this one wrong because that's supposed to be a 0 there because this is the truth labels here. And then we could keep going through there, but we're not going to do that. We want to use some code to do that. So the first thing first, we want a ROC curve because remember that we've got this little list up here. So a ROC curve and an AUC score. What is a ROC curve? Well, if we look that up, so what is a ROC curve? We went through this process, so understanding AUC ROC curve. So if we were to read through this, what we would get is the ROC curve is created by plotting the true positive rate against the false positive rate at various threshold settings. Okay, beautiful. So let's see how we do that. The ROC curve is a way of understanding how your model is performing by comparing the true positive rate to the false positive rate. And if we want to figure out what a true positive and a false positive is, we can have a look at our confusion matrix for that. So a true positive, a model predicts 1 when the truth is 1, and a false positive is just the model predicts 1 when the truth is supposed to be 0. And a perfect model is going to get an AUC score, what we see in a second, of 1.0. So let's see how we do it. So import ROC curve function from sklearn.metrics. That's where it's from. That's where it lived. But we've actually already done this, as with all the other sklearn functions we've been using, right back up the top. Right back up here. So this is model evaluations. Right now in this next section, this next video, we're going to tackle everything from here. So these are, we can see here, we've got randomized search CV, grid search CV, confusion matrix, plot ROC curve, that's what we're about to use, precision score, recall score, F1 score. So these are for our classification model. So let's go down. We can save ourselves a line of code. We don't actually have to import that. We'll come right back down here. We can just go plot ROC curve. Now this is a relatively new addition to this scikit-learn library, which I'm very, very happy with, because usually you had to write these on your own, this function, this plot ROC curve, and calculate. It actually calculates the AUC metric for us, so the area under the curve metric. Let's see it in action. We're going to go plot ROC curve, gs logreg, and if we look up this in the documentation, it'll tell us what it does. Pass it an estimator, which is our machine learning model, pass it x, pass it y, plot receiver operating characteristic, aka ROC curve. So that's what it's going to do for us. Beautiful. So gs logreg, x test, and we want it to do it on the test data set. Always evaluate. This should be calculate. Always evaluate your machine learning models in the test data set. And let's see. Oh, beautiful. Okay. So remember, a perfect ROC curve we've seen in previous videos, we go up to this corner and then across like that, but ours teeters up pretty well. Then we get an area under the curve, so if we calculated all this area under here of 0.93, of course, a perfect model will achieve 1.0. So our model's not perfect, but it's an AUC score of 0.93 when the average of just tossing a coin, essentially, would be 0.5. So we're edging close to a perfect model. Not bad for a model that just came out of the box. All right, the next thing we want to do is a confusion matrix. So let's see that. So confusion matrix. How could we do that? So I think scikit-learn has a function, and I don't think, I know scikit-learn has a function. We can go confusion matrix, and we want to compare the ground truth labels with the predicted labels. Okay, I could just leave it as that. That's a bit bland. We can improve the visualization of this confusion matrix using Seaborn. That's what we want. So we want to go, I believe we already have Seaborn here. Yeah, do we? SNS? Yep, we do. So we've used Seaborn before in this project, so we can go, what I might do is I know ahead of time that we need a bigger font size. So font size equals 1.5. That's just sns.set. Now we're going to create a little function here in case we wanted to make another confusion matrix, because scikit-learn's confusion matrix function isn't up to scratch as of making this video. You could always, maybe that's an opportunity for a pull request. So we go here. Nice and simple. So we're just going to pass it, this function, our test labels and our predicted labels, and then we're going to create a nice looking, plots a nice looking confusion matrix using Seaborn's, we've seen this before, heat map. Wonderful. So we go fig ax equals plt.subplots, fig size equals 3. Oh, shift enter, trigger happy again. Ax equals sns.heatmap, wonderful. And we're going to pass it the scikit-learn function, confusion matrix, y test, y preds. And then we want to add here a not, so annotate, yes, please. Annotate equals true. Then we're going to go C bar, because we don't want a color bar, because I've seen the color bar and it doesn't look too great on a confusion matrix. plt.xlabel, true label, and then we're going to plt.ylabel, we're going to go predicted label. And let's see it. So we're going to go plot conf mat, confusion matrix, y test, y preds. Oh no, what have we done? Font size. ax.set got font size wrong. What is this? Tab? Oh, scale. There we go. Tab autocomplete for the win. Ah, classic. And it's giving us this little cutoff thing here. So we can fix this, I believe, by going bottom top equals ax.getYlim. Yep. And then we want to go ax.setYlim. Make it a little bit pretty. Set ylim, and it's going to be bottom plus 0.5, top minus 0.5. Now, of course, if your confusion matrix came out looking well, you might not need these lines, but it doesn't matter. There we go. We made it look a little bit better. So you can see that the model gets confused, so it predicts the wrong label, relatively the same across both classes. So in essence, there's 4 occasions here where the model predicted 0, the predicted label. So it predicted someone didn't have heart disease when they should have been predicted as 1. So that's a false negative. So it's predicting 0 instead of 1. A false negative, remember, as we come back here, false negative model predicts 0 when the truth is 1. And over here is the false positives. So AKA, we've got 3 instances here where a model predicts 1. Someone does have heart disease when they actually don't. And you can see these are both things that we want to avoid, right? Especially when we're thinking about something as severe or as serious as heart disease. Even predicting when it's not present. So here, if we predict 0, so no disease when it is present, okay, that's bad. But also predicting that it is there when it's not actually there, that's also bad. So that's something that you want to have to consider when you're building these type of models. Is a false negative worse or is a false positive worse? And again, a perfect model would have none of these, but in reality, you're going to probably end up having some sort of confusion here with your model. You're not going to, ideally, these would be perfect across here, across the line. Now, we've done a confusion matrix. We've got that there. We could share that with our boss. We could share that with our boss, a rock curve there. What's next? Classification report. Okay, and it would be great if cross-validation was used where possible. All right, so that's what we might tackle in the next video. Okay, so we've got a confusion matrix, and we've got a rock curve as well as an AUC metric. Let's write this down, actually. Let's communicate with ourselves. So now we've got a rock curve, an AUC metric, and a confusion matrix. So we've got a rock curve, an AUC metric, and a confusion matrix. Let's get a classification report as well as cross-validated, this is a key one here, cross-validated precision, recall, and F1 score. Beautiful. So if we want a classification report, we've already imported the function there, so we can do it. We go print classification report. Now, classification report is going to give us the precision, recall, and F1 score, but let's see it first. Classification report, we can find it by passing it y-test and y-preds. Boom. This has given us everything that we need, right? Cross-validated precision, recall, F1 score. Well, not really. The reason being is because this classification report, it's been on y-preds, it's only being done on one set of test data. So we've got a classification report. It's been found by this, and we can tell that by coming up here, back to where we made predictions. So we only made predictions on the test data set. So if we come back, we only made predictions on here. So what we need to do is a cross-validation score of precision, recall, and F1, which is the values that we've got here, precision, recall, and F1. Now, you might be looking at this going, Daniel's telling me we need to cross-validate precision, recall, and F1. Still not exactly sure. I kind of forgot what's actually going on here, but that's okay. Let's get a refresh of what's happening. We got precision. So precision indicates the proportion of positive identification, so aka the model predicts class 1, which has heart disease, which were actually correct. So a model which produces no false positives, right? So a false positive up here is false positive, predicted 1 when it's supposed to be 0. A model which predicts none of these has a precision of 1.0. All right, so that's precision. Now recall indicates the proportion of actual positives which were correctly classified. So a model which produces no false negatives, has a recall of 1. So a model which produces no false negatives. So remember, false negative is where the model predicts 0. In a binary classification, predicts 0, where it should have predicted 1. So a model with 0 in this box will have a recall of 1, and a model with a precision of 1 will have a 0 in this box. So if our model was perfect, these would both be zeros, and our precision and recall would both be 1.0. And now F1 is a combination of precision and recall. So if our model was perfect and had precision and recall scores of 1.0, F1 would also be 1.0. Now support. Support is the number of samples each metric was calculated on. In our test data set, there are 29 samples with a value of 0 and 32 samples with a value of 1, so has heart disease. And now accuracy, we've seen that before. And macro average, this is short for average, is the average precision, recall, and F1 score between classes, so between these two. So the macro average doesn't take class imbalance into account. So if you have class imbalances, in our case we don't because we have relatively similar numbers of values here. So say for example this was 2 and this was 59, then you would have class imbalances. If you do have class imbalances, pay attention to the macro average. But for the weighted average, is the weighted average precision, recall, and F1 score. So weighted is the key here between classes. So weighted means each metric is calculated with respect to how many samples there are in each class. So aka this metric will favor the majority class, e.g. this will be a high value when one class outperforms another due to having more samples because that class has more samples and it will be given a higher weight. Whew, that was a bit of a mouthful, but you can look up this information in the classification report documentation, so classification report Scikit-Learn. You can also look up each of those metrics that we just covered individually, right? So if you wanted to find out more, actually, we want the user guide. There we go. This is going to tell you some information about the classification report. If you want to search for more, you go precision, recall, F1, and you could look these up, macro average, weighted average, in the Scikit-Learn documentation. But remember, we just said before that these metrics here are only calculated, if we look at our cross-validation diagram, are only calculated on one test split. So what we want to do is recalculate these metrics, but with using cross-validation, which makes them a little bit more robust. So how could we do that? What we might do is wait till the next video. So spoiler alert, in the next video, we're going to calculate these metrics here using cross-validation. So in the last video, we left off saying that these metrics here, precision, recall, and F1 score, are only calculated using one split, train test split. So only calculated using one. But we want to prefer using cross-validation where possible. So that's what we're going to do. Let's make a little heading. We'll go calculate evaluation metrics using cross-validation. We'll write it here. We're going to calculate precision, recall, and F1 score of our model using cross-validation. And to do so, we'll be using, we'll put this one in code, cross-val score. So we've seen this one in the Scikit-Learn section, cross-val score. And if we look it up here, as we always want to do, so cross-val score, what's it say? So it takes an estimator, it takes an X, it takes a Y, evaluate a score by cross-validation. The thing we want to pay attention to here is scoring. So if we go to scoring, is string callable. A string or scorer callable object function with signature, which should return only a single value. Okay, so this is the parameter we're going to use to evaluate our model using cross-validation with different metrics. So we're going to change the scoring string. So let's see that. We'll set up a new logistic regression model instance with our best hyperparameters. what were our best hyperparameters? So let's go check best hyperparameters, because we want to set up one of the best models that we can and then use cross-validation on it to evaluate it. GS log reg dot best params. Wonderful. So now we're going to create a classifier. We'll go here, create a new classifier with best parameters that we found. So CLF equals logistic regression. C equals, we're going to just copy that here. Wonderful. Oops, we forgot the 0. That's a very long number there. And then solver equals, now again, these parameters might be different if you've done your own hyperparameter tuning and found some better ones, but that'll do for us for now. Wonderful. So now we've instantiated a model with the best hyperparameters. Let's use cross-val score along with the scoring parameter to get some cross-validated metrics. So what we do, I've actually forgotten. We'll go here. We're going to calculate, yes, there we go. So we want accuracy. I'll go here, cross-validated accuracy. So we might do 4 cells and we go here, cross-validated precision, cross-validated recall, and then cross-validated F1 score. Wonderful. So let's do that. So we're going to CV AC, which stands for cross-validation accuracy, equals cross-val score, and we're going to pass it our classifier, which we just instantiated here. We're going to pass it all of the X data because we can now, because we're using cross-val score, and all of the Y data. We're going to set CV to 5, and we're going to set scoring to be accuracy. Beautiful. And then we're going to check out what CV AC looks like. And we can take the mean of this, because remember, what has it done? It's evaluated our model over 5 different splits. So if we take the mean of it, right, that's going to get the average accuracy across these 5 different splits. So let's do that. So we go mp.mean, CV AC. Wonderful. So that's our accuracy there. So we might save that actually. We might just override our value. And then we'll go CV AC. Beautiful. And now let's do the same with these other ones. We'll go here. We could just copy the code here. Again, you don't want to get into the habit of copying code. We should really functionize this, but we're just going to keep rolling with the punches, what we're doing now. And by functionize this, I mean because we're doing relatively similar calculations the whole way through, we could just make it function. So there's the precision. Might override this to be precision equals MP mean. And then see it again. Wonderful. And then we can do the same thing here, except for recall. What we might do is be a little bit tricky. Put in spaces here. When you hold command, you can put little cursors here. So if we just change this all to recall. Oh, happy days. Look at that. I got 5 cursors on the go. Recall. Wonderful. Oh, that's a nice recall score. Cross-validated as well. We might do the same for F1. We go here. We're going to change all of these bad boys to F1. There we go. We might put a little space here so our code is looking Pythonic. Wonderful. All right. And so now we've got all these cross-validation metrics or cross-validated metrics that our boss is requesting. It's not really good to just have them here sitting in a Jupyter notebook. Like all of our other valuable stuff is in a nice, neat little table. There's our classification matrix. That looks really good in a presentation, you know? This is something that someone could look at and go, yep, I can see that value is pretty high. I can see what's happening here. Let's do the same. Rather than just having them all spread out, let's put it into a graph of sorts or a visualization. So we go visualize our cross-validated metrics. So we're going to create CV metrics as a data frame. I mean, yeah, we probably really should have functionized this to begin with, but that's all right. Sometimes you have to just go through the old-fashioned way and then realize where you've gone wrong and see how you could improve it. Maybe that's a little extension you could try yourself, is see how you could functionize some of what we're doing here. Maybe it just cross-validates X and Y using different metrics and puts it all into a nice little presentation. All in one hit. That would be a good practice. CV recall, and then we go F1 is going to be our CV F1. Wonderful. We need to set an index equals 0. Beautiful. Then we can create a plot, CV metrics. Now I've done this before, spoiler alert, so I know I need to transpose it. Bar title equals cross-validated classification metrics. And do we want a legend? No, we don't. False. Let's see what that looks like. Beautiful. We're going to put a little semicolon here. There we go. So maybe we could probably add like the numbers on here so people know exactly what they are, but we see our model's doing pretty well on recall. And again, we could probably add our cross-validation results from our random forest model or our k-nearest neighbors classifier or any other classification model that we may have tried during our experimentation phase. Remember, this experimentation phase, it's an iterative process, right? Just going back and back and back and forth through here. So we could add that to here and see which model performs best. But for now, we're sticking with logistic regression. And this looks like something that we could share. So what do we have left now? Well, let's scroll back up to where we put down what we've ticked off. Have we ticked off everything? The things our boss was asking, the things we previously didn't know how to do, but now we've seen them in action. Whew. All right. So we've got cross-validation, precision, recall, yep, classification report, tick, ROC curve, tick, area under the curve, code fusion matrix, yep. The thing we're missing out on here is feature importance. All right, well, let's see how we do feature importance in the next video. All right. To finish off this proof of concept that we're working through of predicting whether or not someone has heart disease, we're going to fulfill the last requirement that our boss asked of us, and that is feature importance. So let's make a little heading here. Feature importance. Beautiful. Now, what is feature importance? Well, feature importance, let's just put a little note to ourselves. Feature importance is another way of asking which features contributed most to the outcomes of the model. And you could also extend it, and how did they contribute? This is useful to know, since we're trying to predict heart disease using a patient's medical characteristics. Which characteristics, for a refresher, we've seen this a few times now, but we'll refresh ourselves. We're using this data here. So, which one of these characteristics of age, sex, CP, all these other ones, cholesterol, phthalac, exang, and if you want a breakdown of what they are, we can revisit our data dictionary up the top. We're looking at here, feature importance. Which one of these contributes, and how do they contribute, or how much do they contribute to predicting the target? So, how would you exactly find it out? Well, finding feature importance is different for each machine learning model. Now, as we saw before with how to tune hyperparameters of a certain model, what you might want to look up, and since we're using logistic regression to calculate all of these metrics, a logistic regression is the model that we found by grid search, by tuning the hyperparameters to get the best results so far. What you might look up is something like this: how to find feature importance using logistic regression. If we go here, I'll look into feature importance using logistic regression, model-based feature importance, how to find the importance of features of a logistic regression model. If you went through this, you could insert almost any model here, so random forest or KNN classifiers or something like that, and you'd find a bunch of different methods. So what we're going to do again is pretend that we've done our research. Our boss has gone, can you get the feature importance of that model? And we've gone, hold on, I'm not entirely sure what feature importance is. So we've gone away for overnight or for a couple of hours, done our research, got our model and figured out, okay, this is how we find feature importance. Beautiful. So that's what we're going to do here. We've pretended we've done this research, but remember, part of being a machine learning engineer, part of being a data scientist, the most important thing is researching and experimenting. It's built into our framework that we're using. Experiments. That's what we're doing here. We're in the modeling phase, really. That we've created the heading for it, but really we're experimenting. So let's figure it out. Let's find the feature important for our logistic regression model. I'll put here a little note. One way to find feature importance is to search for. So you could put in here, I'll put it in brackets, model name, feature importance. That's one way to do it. That's what we just saw up in this little search here. That's what you should try out if you're curious to how to find feature importance with whichever model that you're using. So first of all, we're going to fit an instance of logistic regression. We'll create one with the best params. So gc log reg, best params. We'll see what that is. Shift and enter. Wonderful. And then we'll go clf equals logistic regression. We're going to pass it a c value of this long decimal. Here we go. And then we're going to pass it here. Solver, lib linear. Beautiful. So we've got our clf. So we'll instantiate that. That's our classifier. And then we'll go clf.fit, xtrain, ytrain. Wonderful. And now, through our research, we've found that there's an attribute to our fitted logistic regression model called coef, which stands for coefficient. Okay, and the way I kind of remember this for logistic regression is coefficient kind of reminds me of correlation. But let's see what happens. Remember, we found this through our research. We've looked up how to find the feature importance for a logistic regression model, and it's told us if we're using Scikit-Learn, specifically logistic regression, and if we fit the model, we can call the coef attribute, which gives us the coefficient, right, the value or how each parameter, let's look at our data set again, how each of these independent variables, so the xtrain data set, the coefficient contributes to our labels here, or the target labels. Whew. So that was a bit of a mouthful, but what we're going to do is manipulate this coefficient array so that it looks like it makes sense. Because right now it's just a list of numbers, but if you counted them up, they're actually going to be the same length as what's happening here, these amount of columns here. But let's just twist them together so we're going to match the features to columns. Coefs of features to columns. So this is going to make sense. That's what I'm trying to get at. This will make it make sense. Dict. So feature dict. We're going to create a dictionary and we're going to zip together df.columns. And we're going to list along with clf.coef 0. And let's see. Feature dict. Boom! Look at that. How good is that? So if we go here, we've mapped all of the different variables here to the right column. Let's remind ourselves of what's happening here. df head. So all we've done is we've taken the coef array, right, which is an attribute of our classifier, and we've taken the columns from our data frame, and we've mapped them to each other. So what this is telling us is how much and what way, see, we've got some negative values here, whether it's a negative or positive correlation, how much each of these contribute to predicting the target variable. Whoa, that's a bit of a mouthful then. Another way, visualize feature importance. Actually, I shouldn't have told you that. I should have told you that was a little magic trick that I had. Magician never reveals his secrets. What we're doing is we're visualizing this so we can kind of get an idea of what's going on. So index equals 0, different line. Feature df dot transpose. A lot of transposing plots here, but that's all right. Title equals title. Feature importance. We'll go legend. No, thank you. Whoa, there we go. So, does this make sense? What is happening here? So this, in essence, is how much each feature here contributes to predicting the target variable, whether someone has heart disease or not. You can see that some are negative and some are positive. And now, you might be thinking, we have seen something similar to this, right? Whether one feature is negative and one feature is positive. If it's not coming to you right now, it's okay. It took me a while to connect these two. But if we go right back up here, right back up to our correlation matrix. So this is where I remember for logistic regression, if we want to figure out feature importance, we use COEF because correlation matrix, coefficient, kind of the same thing. Kind of, not really, but you get my picture. So we can see here some different values. So if we got CP equals 0.43, okay, thal-ac equals 0.42, and then we got, what else do we have? Xang equals negative 0.44. If we go down here, now we've got the same thing. So we've got CP equals 0.66. Oh, it's a higher number here. And then we got thal-ac, okay, which is 0.02. We got Xang, which is negative 0.6. So now what we're doing is we're doing model-driven exploratory data analysis. These values have come from building a machine learning model which has found patterns in the data, and it's telling us how it contributes, right, or how it correlates to our target variable. That's what we're looking at here. So, what can we do with these values? Well, let's explore them a little bit and just see if they make sense. So we can see that sex is fairly negatively correlated, like it's almost right here at the bottom. If the value is negative, we saw before with the correlation matrix, it means that there's a negative correlation. Okay, when the value for sex increases, the target value decreases because of the negative coefficient. Let's look at this, see if this actually reflects the data. Let's go sex, let's compare df.target. What do we say? So, which means as the value for sex increases, the target value decreases because it's negative coefficient. So, value for sex increases. So, as it goes up, the target value decreases. That doesn't really make sense when we look at this. Look, so sex goes up, increases, but so does the target value. Oh, you know what? After looking at this, you can see that the ratio is what we're thinking about here. So as sex goes up, the target value, the ratio decreases. So you can see here, if the sex is 0 for female, there's almost a 3-to-1 ratio here. So 72 divided by 24 is almost 3. We look at that. 72 divided by 3. Oh, exactly 24. So it's a 3-to-1 ratio here. And then as sex increases, the target goes down to about a 1-to-2 ratio. See, there's roughly the 50-50 here. Okay, so that's a negative correlation, which means that sex is strongly negatively, or a negative coefficient, sorry, because we're using the coefficient, COEF. We're using COEF up here, the COEF attribute. Now, let's have a look at a positive one, CP, or maybe slope, because we've already explored CP before. So let's do that, PD crosstab. I'm not actually sure what slope is, so we might have to revisit our data dictionary. And again, this is model-driven exploratory data analysis here, right? We're trying to figure out what's going on using the results from our model and seeing if what our model's learnt holds water. So it's saying here that as slope increases, because it's a positive coefficient, that means that the target should also increase as well. So let's have a look. So slope, we got a value of 0, 1, 2. So as it increases, it's from 0 to 1 to 2, does the number of samples here increase? Well, I think it does, because here we've got slightly more here. We've got slightly more there, or we've got almost double there. But then as it gets really high, we've got basically triple people with heart disease. So let's go back up to the top and see what slope is in our data dictionary. Slope. What we might do is copy this so we can come back down. Copy that. We'll come right back down to where we were. Now let's see if this makes sense, right? We've got a positive correlation according to our model, or positive coefficient. So we'll put here, we'll change that to markdown. Oh, that doesn't look very nice. We'll put these as dot points. Slope. The slope of the peak exercise ST segment. So 0 is unsloping. So better heart rate with exercise. Uncommon. Yeah, that is pretty uncommon. Flat sloping, minimal change, typical healthy heart. Okay, yep. And then 2, signs down sloping. So signs of an unhealthy heart. Ah, okay. That's making sense, right? This correlation here, if you weren't a medical expert, right, but you know a little bit about how things go. If you were to say someone had an unhealthy heart and you were to ask someone, well, you know that they potentially have an unhealthy heart because their slope value is 2. Would you say they're more likely to have heart disease, aka having a value of 1, or not have heart disease? Well, according to our model, it's giving it a positive coefficient to slope. So as the slope value increases, it means the model is more likely to predict a higher value of the target. And what's our higher value of the target? Because we're only predicting 0 or 1, the higher value is 1. Wow, now we could keep going with this, but this is something that you could probably share. What is the importance of having something like this? First of all, you find out more. So if some of the correlations and feature importances here confusing, a subject matter expert may be able to shed some light on the situation. So this is something you might be able to take to one of your partners or one of your colleagues and go, hey, I'm not sure what's actually going on here with chest pain having a positive coefficient. Are you able to help me out? Or 2, you could redirect your efforts. So if some of these features offer more value than others, this may change how you collect data for different problems. So see here, these don't really influence. These ones here, age, cholesterol, stress, these are all really low coefficients here. Now that might influence how you go about collecting data in the future. Maybe finding someone's cholesterol level is really hard to do. If it's not contributing much to the patterns a model is finding, you might scrap that in future data collection. And then again, this is the third point, it's less but better, right? So if some features are offering far more values than others, you could reduce the number of features your model tries to find patterns in, as well as improving these ones. So that's what we just continuation, really point 2 and 3 are kind of the same thing. You could combine these in some way or improve these or just make the ones that are offering the most better. This would not only save you on computation by having a model find patterns across less features, you could still achieve the same performance with using the features that offer the most value. So that's something to keep in mind. All right, so we've fulfilled all of the requirements in our project that our boss was asking for. We got feature importance, we got cross-validation classification metrics, yes. We got a confusion matrix, so many different matrices here, my goodness. We've got a ROC curve, we've got area under the curve, beautiful. I wonder if there's anything we're missing out. Well, let's figure that out in the next video. Well, we've completed all the metrics our boss requested. We should be able to put together a pretty good report containing our confusion matrix, a handful of cross-validated metrics such as precision, recall, and F1, as well as which features contribute most to the model making a decision. You might be wondering, why haven't we got a heading for experimentation? So if we come back here, why haven't we gone through this? Right? Well, the secret here is this whole thing, especially from the modeling section onwards, has been experimentation. We've been trying different things. We've been testing out different methodologies. We've been exploring our data. We've been experimenting the whole time. So actually, we've been fulfilling this framework. We've defined our problem. We've looked at the data. We've defined an evaluation metric. We've checked features. We've done some modeling. And the truth is, we could keep going with our modeling, trying to improve it, or trying to improve our logistic regression model that we've left off with, or trying to find another classification model that does better. But of course, things can't go on forever. In practice, in the biz, this is kind of what we'd call a proof of concept, right? We'd go try a few things, we'd look at different data. Once we've done it in a segregated timeline, in a defined timeline, like maybe this whole process took 2 weeks or something like that, we've actually done this in about 2 hours here. So really, don't worry if you're not picking up on things. These processes take a little bit of time. So have we hit? This is where we'd probably revisit our evaluation metric to kind of decide whether we're going to push forward or do we have enough time. We might talk to the client, we might talk to the business we're partnering with, we might talk to some of our colleagues and go, hey, we've tried a few things, but we still haven't reached our evaluation metric of at least 95% accuracy of predicting whether or not a patient has heart disease during the proof of concept. This is kind of where you get to in machine learning, right? As you work through these processes, and there's really no stop to it. And that's what makes it also hard. Well, in our case, we didn't get to 95%, but we did get pretty close, right? We did get to 90% or so accuracy with our logistic regression model, wherever it is, somewhere up here, just over there. So its accuracy, that was about 88% when we cross-validated. So what could you try next? You might be thinking, once you get to this point, you're like, oh, well, I didn't fulfill the evaluation metric. Is everything we've done wasted? No. Well, what we found out in this case, we've shown what doesn't work, at least with the current data that we have, at least with the models that we've had. We've figured out what doesn't work, which is just as valuable as figuring out what does, because now we know, okay, we can try something new. All right. Well, this is really where step 6 comes into its own. So this is where you'd go starting to do your own research, starting to search up different ways of doing different classification problems, building out improved models, different ways of looking at data. What you might ask yourself is, here, if you haven't hit your evaluation metric yet, ask yourself some things like, could you collect more data? Because remember, machine learning models love to learn on more data, so could you collect more samples? Right now, we've got about 303 or so of patient samples. Could you double that? Potentially. Maybe you have to talk to a subject matter expert. Maybe you have to talk to a doctor or go back to the client you're working with or whatever project you're on and go, hey, is there any way we could get more data to enrich this data set? Or could you try a better model? You might be asking, well, we've used a logistic regression model and I've looked at here, where is it? The Scikit-Learn map. There aren't too many that we could try again. That's where you might have to start doing some research. You might have to look into something like CatBoost. We won't cover for now. I'll just plant the seed. I'll write it here, like CatBoost. That's some extra curriculum for you, like CatBoost or XGBoost. These are things you might want to look up, right? So you might want to search those two things. What else is there? Well, okay, if we have tried a logistic regression model and could we improve it? So could we improve the current models? In brackets, beyond what we've done so far. So maybe we've done a little bit of hyperparameter tuning using grid search CV or randomized search CV. So maybe we want to try a little bit more, see if we can squeeze a couple of percentage points of accuracy out. Again, you might be thinking, well, this doesn't seem very structured. And the truth is that it's not. It's all about minimizing your time between experiments and machine learning. So let's say we did meet our evaluation metric. If we did, so if our model is good enough, how could you export it and share it with others? So maybe we go here, Scikit-Learn, how to export a model. And then we'd go here, model persistence. So say we did want to send a model to a colleague or a client or something like that. You might want to look up here, how to send a model. We've done this in the Scikit-Learn section. So if we go here, if your model is good enough, you have hit your evaluation metric. How would you export it and share it with others, right? So the real takeaway point here, the key to remember is we've gone through this entire framework now. We've got some data, we've defined a problem, we've explored that data, we've defined an evaluation metric, we've looked at the features of our data, we've done a bunch of machine learning modeling, and really this whole process has been an experiment, and we've used the tools that we've learned so far, all within one beautiful Jupyter notebook. And now, the final takeaway is that there is no real answer to what you could do next. It's up to you to ask questions and to start figuring these things out, to start searching, to not be afraid to be wrong. That is the biggest thing that will hold you back in machine learning. If you don't ask questions, if you don't go through things like this, or if you don't reach out to other people, if you don't ask the community, if you don't look on Stack Overflow, if you don't find examples, you're not going to improve. Finishing off this project, what you could probably do as an extension is to ask these questions here. Maybe we can't collect more data because the data set is fixed, but we could potentially try a better model like CapBoost or XGBoost. That's maybe something you could try. And you could also try to do some research on how we could improve the current models using hyperparameter tuning. But congratulations, you've just finished. If you're following along, you've just gone end to end on a complete machine learning classification problem. Isn't that amazing? Predicting heart disease using machine learning. I hope you're starting to see. Actually, this is probably the more important point. Rather than going on to what's next, if you've followed through with this and you're still wondering, you're going, holy goodness, Daniel, there is so much here. I don't know how I could remember all of this. Do not worry, because I'm still in that position, right? Even working as a machine learning engineer, I still run through that every single time. Like, oh, what can I do? I always end up on rabbit hole searches like this and then bring it back into a notebook. And trust me, the first time you build a notebook, like something like this for a machine learning problem, it probably won't look like what we've got, right? Ours is pretty neat, right? So it's pretty structured. It goes through the framework step by step. Your first time, it will probably have things all over the place, and that's good. That's good because it means you're trying new things. What can you do from here? Check out this code, or it'll all be in the resources section. It'll all be in an attachment somewhere that you can access. Go through it. If you can find another classification data set somewhere on the internet, you can find those pretty easy. So classification, machine learning, data set. You can find a whole bunch. So data sets, UCI machine learning repository. That's what we found the heart disease data set right back in the beginning. That's where we found this. Maybe you could find some more. Maybe you could find some on Kaggle or KD Nuggets. There's a whole bunch of different resources. So maybe you could find another data set and then go back through this pipeline that we've created for a classification problem, just now with a different data set. And you could have an end-to-end, insert your data set here, classification problem. But that's going to wrap up project 1, end-to-end classification. If you have any questions, feel free to leave them. Otherwise, I'll see you in the next set of videos.